Como las 7. Ándale, como las 7:15. ¿No? Que diciendo que ayer se me había puesto. Ayer se me había puesto. Nosotros chavos. No sabía. Ah, yo no. La música. Sí, sí, todo bien.
¿Estás del coanfitrión a doctor Mayoral? ¿Es esa?
Sí, 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 sí. O sea, esta computadora es aquí
Está
la que dice
como el doctor Mayoral.
Ah, ok.
Sí. Entonces sí ya tienen el coanfitrión.
Sí.
Pueden hacer lo que quieran ya.
Ah, perfecto.
¿Sí?
Ok.
Sí, si quieren grabar, lo pueden grabar a la nube. Y ya después les paso la grabación, si quieren. Okay. De todos modos, como se está transmitiendo a YouTube, se queda grabado en YouTube. Entonces, pero bueno, ya ustedes pueden controlarlo como quieran.
Perfecto.
Bueno, Luis Arellano, ¿qué tal? Mucho gusto. Mucho gusto. Hola. Bueno, ¿qué tal?
Hola, Mauricio.
Ayer te agarramos. Sí, ayer sí estaba yo así en blanco, pero bueno es que ya está todo listo. Sí, ahorita ya se está transmitiendo, a YouTube, cualquier cosa. Perfecto. Sí, ya en unos minutos. Igual yo tomo tu contacto. Sí, ok, perfecto. Yo voy a estar ahí monitoreando, pero les digo, tengo otro.
Que si a las 8:30 va a empezar a hablar él o va a haber unos minutos como de introducción del doctor John, me está preguntando.
A las 8:05. A las 8:03.
8:30.
Es que a las 8:35 ya habla él. O sea, pero que esté ahí presente, que luego va a hablar.
Ok. Si quiere aquí le escribo. Sí.
Nada más se abre el evento, se llevará 2 palabras y después entonces a las 8:33. O sea, en teoría a las 8:30 nada más lo vamos a presentar.
El más alto es el doctor John Stewart. Después el que está a su izquierda es el doctor Moreno. Después el que está enfrente es el doctor Mónica. Bueno.
Para que no... No, si quieres. O es para la mesa redonda, ¿no?
Entonces nada más ahorita. Perfecto.
Los dos funcionan, muy bien. Good morning, everybody. Good morning. On behalf of the Mexican Society of Earthquake Engineering, it is a privilege to welcome you to this event, Resilience of Strategic Infrastructure to Extreme Events. We are grateful to the Institute of Engineering, firstly, for hosting us here at the Torre de Ingeniería, and for co-hosting tomorrow's program, also the Tech of the Monterrey. My sincere thanks as well to our partner institutions today, the Institute of Geophysics at UNAM, UCLA, UC Berkeley, USGS, and also the Mexican Society of Geotechnical Engineering. Allow me to acknowledge in particular Dr. Rosa Maria Ramirez Zamora, who couldn't make it in time here, but she's our main host here, so anyhow, thank you. To Dr. Juan Manuel Mayoral, whose leadership has been instrumental in bringing us together here. And thank you for your support and vision to make it possible for research, professional practice, and public service to meet in one room. So why are we here? Mexico knows perhaps better than most countries the human, social, and economic costs of major earthquakes and other extreme events. As we mark 40 years since the 1985 earthquake and also recall 2017, our aim is not only to remember, but to learn better, decide better, and build better. When we speak of strategic infrastructure, we mean hospitals, schools, water and power systems, bridges, transit lines, data centers, and buildings that can sustain critical functions. And the bar is continuing to operate for all these infrastructure under extraordinary demand and with constrained resources. That is resilience, the capacity to anticipate, withstand, recover, and adapt. In today's program, we will see a few presentations. We open with Dr. Jonathan Bray on how earthquake reconnaissance has shaped the evolution of performance-based design. What we observe in the field must close the learning loop in our manuals, codes, and projects. We then turn to ground motion prediction models used in Mexico and Mexico City with Dr. Mario Ordaz and Dr. Eduardo Reynoso, and we will examine assumptions, scope, and limitations to designers know when and how to use each tool. After the break, Dr. Jonathan Stewart will address value of Mexico City site response and its implementation in ground motion models. We follow with Dr. Morgan Moschetti, right, from the USGS on the US National Seismic Hazard Model, model selection and combination, treatment of uncertainty, and the challenge of discontinuity across the US-Mexican border. We conclude with a technical discussion with all our speakers, and we will add a few more afterwards. The focus is implications for design practice. Oh, I'm sorry. That is yours, actually. I'm sorry. So what is our goal today? Let me propose three deliverables for these sessions. A shared reference framework on the seismic hazard and ground motion models recommended for different Mexican contexts, including minimum criteria for selection and documentation. Define priorities for applied research and instrumentation to reduce dominant uncertainties, site data, time series, spatial correlations. And the commitment to collaborate among academia, international academics, to share their knowledge here and to keep sharing it in the future. So that is pretty much one shorter introduction to our speakers. Thank you for your generosity. Thank you for coming here. To our colleagues visiting from abroad, thank you for sharing methods and lessons we can adapt here. And to all attendees, researchers, students, we encourage active participation. Ask, challenge, question everything that is being said here. The quality of our conclusions will come from the quality of this exchange. With this collective expertise, I'm confident we can take meaningful steps to Mexico's strategic infrastructure and make it more functional and more recoverable in the face of extreme events. Well, welcome everybody. I hereby open the proceedings and without further ado, invite our first speaker, Dr. Jonathan Bray. Can you just unlock the... Otra vez.
Good morning. Can you see my presentation and hear me well?
Yeah, I'm just going to introduce you shortly. I'm sorry for the delay. Dr. Jonathan Bray is the faculty chair in Earthquake Engineering Excellence at Berkeley. He's a registered professional civil engineer and has authored more than 490 research publications. He created and led GEAR. He is a member of the U.S. National Academy of Engineering and received the HBC medal. Welcome, Dr. Jonathan Bray. Thank you.
Thank you very much for inviting me, and I apologize for not being able to be there. We have earthquake threats in California as well, and I'm actually going to go into the classroom and teach our students about geotechnical earthquake engineering after this lecture. I would also like to dedicate this lecture to my late friend, Professor Juan Pastana, who unfortunately passed just 2 days ago. He was an incredible engineer. He actually performed earthquake reconnaissance of an earlier earthquake in 1999 that was in Mexico, and he had tremendous involvement in many countries, and I know Mexico as well. So it's a great loss to have lost him so early. I will talk about post-earthquake reconnaissance and its role in developing performance-based design. And much of this was done through the National Science Foundation Geotechnical Extreme Events Reconnaissance Organization. Now, post-earthquake reconnaissance is important for our profession. As you know, earthquake engineering is an experience-driven field. You can't replicate all of the characteristics of a natural soil deposit that may be hundreds to thousands of years old in the laboratory. And therefore, from the late Professor Harry Seed and outside of earthquake engineering, Ralph Peck and Terzaghi, field observations have been a key cornerstone of our profession. They shape our understanding. And in fact, they provide the data that we rely on for many of our design procedures. Liquefaction triggering is still as much as we love to do theory, the empirical basis is the most rigorous method applied in design. And then when we get into performance-based earthquake engineering and we have to estimate the effects of liquefaction, which we can all argue is the more important problem to answer, things like lateral spreading, we still have tremendous challenges to be able to duplicate that in our computers with the sophistication of the process, the movement of water. We need to get there, but until we get there, empirical methods will be the standard. But it's personal to me. I was at Berkeley on October 17th, 1989, and I, like many people, went home through the Cypress structure to my apartment in downtown Oakland to be able to watch the baseball World Series between the San Francisco Giants and the Oakland A's, the Bay Series. And instead of being in traffic at 5 p.m., I was in front of my TV when at 5:02 that earthquake struck. And one of the most devastating things was the damage of the cypress structure. And this is showing some of the collapsed structures. And the structural engineers in the room and structural engineers who investigated this will talk about the lack of ductility, confinement. There were clearly deficiencies in this structure. But performance-based earthquake engineering is not just being able to predict that this structure would have issues. It's also important to show that there was section of that badly built, vulnerable structure that did not fail. And we often focus on the failures, but we also need to focus on the successes. 42 people died on that Tuesday. It would have been an order of magnitude greater if we just didn't have that baseball game, which took people off the highway and in front of their TV. If you investigate and you look at the development of the San Francisco Bay Area, Oakland was being developed, and of course they started on the firm ground, but as the city grew, they put fill on top of soft clay, and that's the area that collapsed. The area on the stiff soil did not collapse from this earthquake that was about 70 kilometers away. This is a recording of aftershocks on one aftershock on bedrock, the stiff soil, and the soft bay mud, and you can see the amplification effect. And again, you know about these things from 1985 and 2017, and every earthquake that hits Mexico City, the importance of soft clay response, which obviously is intensity dependent. In this case, it led to an amplification of the ground motion intensity, the change in the frequency content, as well as a extension of the duration of strong shaking. In San Francisco, there was also soft clay in the Marina District, and there were soft stories that collapsed there that did not collapse on the Presidio, which is on rock. So we have this classic, which we've seen over and over again, about rock versus soil. A fire was initiated on that day because of the earthquake, and that's the place to go to fly a kite. If you want to take your son or daughter to fly a kite in the Bay Area, the place you can be guaranteed having a stiff breeze is the Marina District. I think there's 8 days out of the year when it's not blowing with tremendous gusts and wind force. This just happened to be lucky that this was one of those days where the smoke went straight up, and they were able to actually mitigate, basically arrest this fire in this location. They were very close to pulling back and fighting the fire and letting this area burn, which when I first came to the San Francisco Bay Area in the 1980s, I would meet with elderly people and I would talk to them about the 1906 earthquake. And they always corrected me and said, it's the 1906 fire. And it's a reminder that earthquakes may start the fire, but these things that we often call secondary hazards or following hazards, they are not following. They are the primary effect. What devastated the city of San Francisco was the fire following that earthquake. What devastated Tokyo in 1923 was the fire following the earthquake. So we always need to be mindful of these hazards that follow the earthquake. Then I had worked as a professor at Purdue. I came back to the Bay Area, and then we had the 1994 Northridge earthquake, which had a lot of similarities to the 1971 San Fernando earthquake, and a lot of information in terms of performance of infrastructure, slope stability, and facilities, including the hospital, the Sylmar Hospital. At that time, the busiest highway in the United States of America was the Santa Monica Freeway. And one of those sections collapsed. Now, I think this is important. The other sections, the other overpasses, did not collapse. And so they need to be investigated to ensure that our methods can say that they did not collapse, and then be able to say that this area did collapse. And why did it collapse? Again, the same issues in terms of structural deficiencies were present at the other overpasses. As you well know from reading this word, it's the swamp. And when investigated, the soils here were a little bit softer, and they amplified the ground shaking from the more distant fault rupture that was in the it was in the San Fernando Valley area, and that contributed to the failure of the system. So again, side effects permeate almost every lesson that we learn, the effects of the ground. Then we had the 1995 Kobe earthquake, and it was devastating because unlike those two earthquakes in California that happened at times that were beneficial for saving lives, on a holiday or on a baseball World Series, this struck early in the morning, and it was close. It wasn't distant. It was close to the urbanized area of Kobe, and there was devastating effects. And there are a number of lessons, but one of the more important lessons was the reality of the intense forward directivity near fault ground shaking. We saw that in 1992 in the Landers earthquake out in the desert in California. But this was now seeing the devastation. If the ground moves a meter in this direction and moves back in the fault normal direction, this can lead to actually these kinds of failures that we see here. As I flew over this place in a helicopter to do early reconnaissance, I was amazed at the damage to the port facilities. The port island and Rocco Island, these constructed islands where they would gently place the sand on top of the soft clay so they did not get a static failure. They were prime candidates for liquefaction. They were worried about an earthquake that was further away and designed these systems for 0.1 G. They did not design them for 0.5 G from a near fault event. And there was massive liquefaction, loss of infrastructure, and this city where 20% of the cargo came in and out of this city of Kobe, they lost all, they had 186 berths, they lost all but 8 berths. And the only berths that survived were the ones where someone had heard about the liquefaction threat and had done ground modification to improve them. And then there's always a surprise. And we had worried about deformations and racking of underground structures and what a ground motion and a softening of the soil due to liquefaction, how that might affect that. And here's a subway station. I was one of the 2 people on the U.S. team, Tom O'Rourke and I, with Liam Finn, were able to go in and see the damage of this subway station. And that's a reminder that we need to ensure we have ductility in these systems as well. But probably the most devastating thing, again, was the fire. Of the 6,000 plus people who died, it was the fire that consumed the majority of the people that led to death. And one of the saddest things I've ever seen was seeing a young woman lay flowers next to pictures of her parents in a burned out area to pay respect to them because they had died in the fire. And it's a reminder to take this serious. Fortunately, these events don't happen that frequently, but when they do occur, as you know from your history in 1985 and 2017, they can have devastating effects. And it's a somber reminder that we need to do better in terms of being able to identify systems that are vulnerable and fix them, repair them before the next event. Now, over the years, we've learned and applied certain principles of reconnaissance. Number one is safety. It is so important to learn, but not at the risk of anyone. There's an appropriate time to respond after the life-saving mission is over. And then when we move into areas, we need to be mindful of safety, and we cannot forget that. We also need to be kind and ethical, and remember the people have just gone through a tremendous event. We need to work as a team, and we need to work internationally as a team. So gear has expanded beyond the borders of the United States of America, and we always participate. Juan Mayor participated in our earthquake reconnaissance. In fact, we participated in his earthquake reconnaissance, is the better way of saying that. It's very important to step back and get an assessment of the overall damage and then identify the key opportunities, because that's where we're going to advance the profession in terms of performance-based earthquake engineering. And we have to ask ourselves, if we invest the time and the resources to document this case history, will it affect the profession? Will it advance the profession? If we have a loose, saturated, clean sand out in the middle of nowhere and it's shaken at 0.4 G, we don't need to investigate that because we know it's going to liquefy. We need to look at maybe silty sands or clayey silts, and we need to look at ground motion levels that are at threshold between triggering and not triggering. We need to look at the effects of liquefaction on infrastructure. Those are our focus areas. And we remind ourselves, one well-documented case history where we invest maybe 4 to 6 hours by a team of 4 people is worth more than thousands of photographs of damage. We've moved from taking pictures of earthquakes to documenting them so that they become a well-established case history that's a landmark case history that we can use to guide our analysis and our insight. What has revolutionized the field is remote sensing, UAVs, LiDAR, structure for motion, so we can do a better job than we did with the old tape measure. It requires systematic, geocoded collection of perishable data. And then very importantly, we naturally want to solve problems. We're engineers, but we can't do that. On an earthquake reconnaissance, we have to think of all the possible mechanisms and all the possible things, and then we need to actually just collect the evidence. If we say, this is a lateral spread, you'll collect data to convince yourself this is a lateral spread. Les Harder and I were at a site where we thought this must be a lateral spread. But by going through all of the data and collecting everything, say, there could be ground deformation from faulting here. In the end, the two abutments of the bridges in Taiwan moved together, not because of a lateral spread, but because of ground deformation over in the hanging wall of that fault rupture. So collect the facts, thinking of all possible mechanisms, and then you have time later to figure out the why. And I point this is we're always looking for something that we haven't seen before. I had not seen, and I don't think the profession had seen, a well-documented case of a bridge that underwent liquefaction-induced vertical settlement with liquefaction, as you can see here in the bottom, along the shaft of this drilled pier that led to about 0.8 of a meter of settlement. And so these are the things we want to say. We have infrastructure throughout Mexico and California that are bridging areas that have liquefiable soils. How do we analyze this phenomenon? It's good to have this case history to calibrate our methods. It's so important. And early on, I landed in Turkey in August of 1999, younger me at that time, a little slimmer me, with J.P. Bardet, and meeting Darren Ural, who was a professor in Turkey at the Istanbul Technical University. We immediately got into a plane, fixed wing on top, so we could go around and see things like Adapazari. In Taiwan, we only had access to helicopter. You can see Steve Kramer, J.P. Bardet, Norm Abramson, Les Harder, and myself. But obviously, this is 9.1 meters of offset. This is a person for scale. There's things you need to do to see the ground. But now everyone can be afforded the opportunity. You had to typically, in fact, Les Harder got on there because he brought money. It's like this was expensive. And so if you could bring money from your organization, you could get on the ride. Now you can see the fault rupture here from the 2014 earthquake. What has changed is every team should be equipped with a UAV and be able to get that situational awareness and see where the deformation is, where it may interact with structures, and be able to collect that. And if done well, with ground control, this can also be turned into a map of deformation from using structure for motion. Remote sensing is critically important. We would not have known about the Las Palmas gold mine failure in Chile during the 2010 earthquake if we hadn't seen this remote sensing. This flow slide killed 4 people. It's of interest because we don't want earthquakes, but if an earthquake occurs, we want to be able to develop back estimates of the post-liquefaction residual strength of sands, silty sands, tailings materials. And there's very few case histories that provide that empirical evidence to make the call on whether the post-liquefaction residual strength ratio is 0.08 or 0.1. And that can be a difference between unsatisfactory or satisfactory behavior. Google Earth changed things. When I went to Turkey in 1999, we scoured for information about maps. Just when we hit Adipazari, how are we going to document the damage? We didn't even have a base map. But you go to Christchurch in 2011, after the Christchurch earthquake, and just 4 days afterwards, you can see the ejecta, you can see this collapsed building, you can walk the ground and be there virtually, so that when you physically get there, you hit the ground with your feet running. And then structure for motion, with good ground control, which is important. Photographs can then take pictures of places that it's not safe to walk on, like this partially collapsed bridge structure, to collect that key data. And then LiDAR has been tremendous because these systems were incredibly expensive. Now they are much more affordable, and you still want to take your measurements by hand because there's always shadows and deficiencies, and you always want to cross-check. But to be able to have a LiDAR system essentially take a picture, which is not a picture, it's got every pixel with its XYZ coordinates, and be able to turn that into this kind of deformation. And one thing that was special about the 2023 earthquake in Turkey is this is the first time I had seen buildings punch in and actually drag down the soil, so that we had this kind of a hogging behavior. Sometimes there was a building in between that was actually damaged by the big structures settling more than the actual structure itself. So we need to start thinking about structure, soil, structure interaction, and the interplay of buildings of different sizes within the urban environment. And your earthquake in 2017. Social media is capturing things. We go to a failure and we wonder what was the initiation. And it's very difficult when you see a pile of rubble to back figure what happened. But now we have our citizen scientists collecting data that is allowing us to go back and say, maybe I've got enough information from these pictures, along with if there's instrumentation, as well as the plans, to be able to look at that structure and see the initiation of failure, and not have the questions and doubts that we had before we had these kinds of images. I wanted to then finish just talking about 3 earthquakes where they've propelled us forward. And I can't really talk about this without talking about Adipazari, which is island market. So again, the name kind of implies it's in softer soil. And I highlighted all of the Turkish engineers that worked with us, who really led us in terms of these, and unfortunately respect the 18,373 people who died. Adipazari has rivers that have meandered over time and laid out sand deposits. And when we looked at the damage statistics, the red zones, more than 45% of the buildings in that district were heavily damaged. And then, of course, there's the rock area, where fewer than 5% of the buildings were damaged. And then we have areas that are 5 to 15, 15 to 30. can we explain those patterns of damage? And so actually Professor Stewart was one of the people who worked on this with me, and that whole team. We couldn't document all of the buildings, and so we did transits across, and we did parallel, because the infrastructure changes when you're on a main boulevard and you're not on a main boulevard. This is just one of those lines where we use the Coburn and Spence characterization for structural damage, no damage, architectural damage, minor structural damage, and then significant structural damage, and then partial and collapse. And then we looked at ground failure, no ground failure, minor, moderate, severe, and mapped that in a very organized way to collect that data, because then these structures are gone. Now that you have that data through National Science Foundation funding and funding from the state of California, we're able to do cone penetration tests. We're able to do properly done energy measured SPTs and the following summer. And then we could go and say, our method said this was non-liquefiable soil over thick liquefiable soil. This was liquefiable soil over liquefiable soil. So of course there's more ground failure there. And this was non-liquefiable soil. And so we can get confidence in our methods. We also noticed that badly built buildings will fail on good soil, but the rate of failure is more on the liquefiable soil. If a structural engineer needs liquefaction to save their structure, they shouldn't be designing structures. And so I do not ever want to use base isolation as a concept for saving a structure. And this is proof that liquefaction and ground deformation under a structure that's being strongly shaking can actually damage a structure at a higher rate. We had to change something to make our methods work. We were using what was known as the modified Chinese criteria, which looked at the percent of soil passing the 5 microns. And the size of the mineral doesn't matter. It's the mineralogy that matters. And so a better index, which we use now, which we did not use in the Yao et al. 2001 state-of-the-art liquefaction triggering method, but what we use now is a PI based, because plasticity index brings in mineralogy, something that Casagrande probably told us back in 1937. Then we go to New Zealand. I was actually doing centrifuge tests, which I think are incredibly valuable, at the centrifuge facility at UC Davis. And it's a lot of work to put this thing together. And so you don't just shake it one time, you shake it with a further away, lower intensity motion, then maybe a more intense motion, then a different motion. And I left Davis and went to New Zealand because they were doing full scale 1G shaking table tests on the island, the South Island of New Zealand. And it's a terrible thing to have these events. It'd be a terrible thing not to learn from them. In fact, the tagline for gear is turning disaster into knowledge. So we had the farther earthquake cause massive liquefaction in the city, mainly in the eastern suburbs, but no one was killed. And then this closer in 6.2, just a few months later, killed 185 people. And then they had another aftershock, and then another aftershock, and then another aftershock. And so this is an incredible opportunity to learn, because there's some sites that liquefied in all of the major events. There's some sites that never liquefied. There's sites that liquefied in 2 of the events, but not 3 of the other 3 events. One of the key issues here is this city was largely developed after the gold rush in New Zealand in the late 1800s. A geologist named Black had mapped the streams that then were covered up as they turned Christchurch from a swamp to a city. Well, those buried stream channels reemerged when strongly shaken during the 2011 Christchurch earthquake. And I'll focus on the CTUC building right here, which we're going to find that this stream actually comes all the way through and affects the performance of this building. Very quickly, we saw a lot of damage along this, and we decided let's do closely spaced CPTs across this feature. And this is just showing section BB, which is the left side. And there's ground that did not liquefy because it's dense below the water table. And here's the buried stream channel. And that edge of that buried stream channel cut across the southern part of this building. We had used, in that time, did not have a LiDAR system, but I had laser levels. And by using laser levels within this garage, we were able to get measurements that were probably plus or minus 10 millimeters at most. We actually did 2 surveys to get some redundancy and check the accuracy. There was a pipe that displaced 60 millimeters relative to this building that did not settle relative to the free field. This building did punch in 60, 70, 80 millimeters, but it was over the last 2 bays, which is what was crossed by that buried stream, where we had the significant settlement and the significant angle of distortion, which led to the structural damage and led to the ejecta. The great thing about a CPT in this environment is we had decided we were going to do a CPT here, some other CPTs on the other side. We had several sites we wanted to investigate, but when we on site saw that this CPT on the northern side of the building was very different than the CPT on the southern part of the building, we put in an extra CPT. That's why it's number 28. And the idea is this ground condition go up to here, or does it stop short? And we clearly see that this buried stream is under the southern part of the building, but not the middle and not the northern part. Now, with that kind of information, now we have the time to get good estimates of the input ground motion, calibrated against strong motion station recordings, and then run those ground motions up through our characterized soil layer. In this case, we use PM4 sand as our material for this liquefiable material. We put in the actual shallow, loose soil that was the key element. We look at the free field sediments and the enhanced or the increased amount of sediment due to the shear below this southern footing, which is not present under the northern footing. And so we make estimates of what we think we should have seen, and we actually look at the settlement, and our calculated settlements, which are shown here in red, do not capture the measured settlements. And I think that's an important thing. The method that we were using, the FLAC analysis with PM4 sand, captured bearing capacity mechanisms. It did not capture ejecta. So if the red line matched the measured settlements, it would be a bad analysis. But we went back and looked and said, well, can we estimate the shear-induced settlement? And from our survey, we were able to do that. We were able to measure the shear-induced settlement. So always think of key mechanisms and realize typically no numerical method doesn't capture all the key mechanisms. Make sure you capture the mechanisms you can capture, and don't pretend to capture the mechanisms that the method was never intended to capture. With these case histories in Christchurch, and I'm highlighting the CTUC building here, and case histories in Turkey, we're able to get observations of how much shear-induced settlement, and we can compare that against this method where we did many analysis and then did regressions to come up with a method to be able to estimate the liquefaction-induced shear displacement. And of course, one should never use a method, no matter how elegant it is, unless it's been validated against field case histories. And the field case histories are there because we've done our post-earthquake reconnaissance. And so this was informative to developing a method to estimate shear-induced building displacement. But it had been some time since people had investigated volumetric ground settlement, and it had not been done in a probabilistic manner. So that needs to be looked at. And nobody was bold enough to try to estimate ejecta-induced settlement, which is probably a challenging thing that still requires additional work. And so following that, I worked with Franklin Alea, who's now a professor in Lima, Peru, and pulled together 205 case histories. We were able to take advantage of previous earthquakes, gear reconnaissance, the liquefaction project. Without that data, we couldn't develop these 205 case histories. We had sufficient number of case histories to break them into natural sites and hydraulic fills. You know, human-built fills and natural fills, they should be different. And this is a great example where, you know, a CPT is not a site. A site is got similar ground conditions. It's great to have multiple CPTs to be able to characterize that ground and include that as part of the spatial variability and have good measurements of the post-liquefaction settlement. So obviously you have to have the measurements before the earthquake, which they had earthquakes in 2013. So they had been doing surveys. So we had good pre and post surveys. We had updated what Ishihara and Yoshinami had done, which was based on one data set for one sand, really good data set, but only on one sand, with dozens of other soils to establish this new model. But that model, which can estimate the volumetric strain, which can give you an estimate of the displacement, has to be modified to be calibrated for, is it a hydraulic fill? This number should be about 1 because the sands in the lab are similar to the sands in the field that are built by humans. And it's got to be different for natural soils. And then we also had a soil behavior factor and a magnitude factor. And importantly, when we did the regression analysis, we found that there was a lower standard error in making the estimate on a hydraulic fill because they were tended to be more uniform, whereas natural soils, which are more heterogeneous, had a higher standard deviation. Now on to ejecta. And when you think about ejecta, this is after an earthquake has occurred. There's not a pipe break there. This is the high pressure water finding its way through the cracks in the crust to come up. This is really a fluid mechanics problem. And so we developed a liquefaction demand parameter that looked at hydraulic conductivity as a weighting function, as well as the excess hydraulic head over that which is necessary to bring the water to the ground surface in a meaningful way. And then we realized the crust matters. And so the stronger the crust, the thicker the crust, you're going to have less ejecta. And so we're using liquefaction demand and crust resistance to develop this graph. The liquefaction severity number developed by Van Balagoy et al., which I was one of the people who worked with him on that, does a good job, but it was missing things. And so using this chart, we were able to actually get better true positive rates. And in fact, the number one reason I developed this is the misestimate by LSN and NLPI and other parameters on stratified silty soil sites. They all suggested you have a lot of ejecta, but we saw very little ejecta at silty soil sites. And this method actually captures that phenomenon. You should expect less ejecta at highly stratified sites. At thick, clean sand sites that are all hydraulically connected, you should expect a lot of ejecta. And then in the end, the consequence matters, not just whether there's manifestations and how severe the manifestations, but we were able to use some very careful work done by Zorana Mishek, who's now a professor at the University of Delaware, to actually put these and correlate the ejecta categories to estimates of settlement. So now you have a way at least to get a ballpark estimate of when ejecta will not be an issue and when it would be a little bit of an issue or a major issue. But there's more work to do. I went to Turkey after the 2023 earthquake, and I saw devastation like I had not seen before. The official count is 53,537 people dead in Turkey. It had to be much more than that. This is in the city of Antalya where all these buildings were collapsed. Think of the dozens and hundreds of people who died. Then you go to Gobasi and you see things that you saw in Adapazari, but then you see things I hadn't seen. One of the reasons I went all the way to Gobasi, I wasn't going to go there, is I heard that there was in the free field, I'd seen this next to buildings, but I had never seen it in the free field, ejecta that had plasticity indices in the range of 9 to 14. And then we got to think about flooding, because the city of Iskandar went down because of liquefaction due settlement. I was there when a normal storm came in and flooded 2 blocks into the city. And so how are you going to make that city resilient when you've lost ground and you've got this flooding effect? So in closing, turning disaster into knowledge, well-documented case histories advance our understanding. This collaborative approach where we have standards for guidelines and standards for collecting data in a systematic way is critically important. Google Earth has changed the way we see the world. I can look at the ground virtually before I put my feet on the ground. But we have to take advantage of these incredible tools we have now, such as LiDAR, structure for motion. Everything should be geocoded. We didn't have that in the early days. You weren't allowed to participate in the 1999 Turkey earthquake without bringing a Garmin GPS 3 Plus device, because we wanted people to go to the same location and make observations. And that's critical for sharing and archiving data. And thus, I think it's clear reconnaissance of these events is necessary because it leads to the new methods that allow us to do performance-based earthquake engineering. Thank you very much.
Thank you very much, John. Thank you for this very amazing presentation. We'll have some time for questions. I don't know if someone in the audience wants to ask something to Professor Chombre. Yes, could you give her the microphone? Give him the microphone. Thank you. Thank you, Mario Rodas.
Thank you very much for your presentation. One thing that I have in mind, and it bothers me a little bit, is that it seems that whenever we go on a reconnaissance a trip for structures, we always seem to find a reason for the collapses, and we basically know why the buildings collapse, etc. And therefore, we don't learn too much because we know what happened. But what about finding out why so many buildings did not collapse? Do you think that should be part of the? Do you think that could teach us more?
Yes, we have to look at buildings that are fragile in our minds before the earthquake that survived, and we have to be able to analyze those, and that's critical. I earned my master's in structural engineering. I started off as a structural engineer and then later decided to get my PhD in geotech. Some of the best reconnaissance have a structural engineer and geotechnical engineer walking together, because there have been failures where the structural engineering team, without a geotechnical engineer, says this failure is because of this column and this beam and this location. And then the geotechs go there later and they go, but there's some liquefiable soil at this site. Might that have taken the spread footings and caused some extension or differential settlement that actually contributed to the failure? And so I think soil structure interaction is one of the key areas where we need to make advancements. And that cannot be done without structural engineers and soil engineers interacting together and documenting case histories. I worked with Jack Maley. I've worked with other structural engineers to try to see a building together. I learned things from the structural engineers because I've left that profession. They learned something from me. And in the end, the ground shakes, the ground deforms, and that contributes to whatever happens to the structure. And I think it's important for us to work together on failures and non-failures.
Thank you, John. Yes, we heard this morning the word collaboration, international collaboration many times. I think we should do that and learn from earthquakes that happen all around the world. Is just the easiest way to know how we can improve our designs. I have a question, John. In terms of performance-based design and liquefaction, what are the latest documents that we can actually start applying in practice that incorporates all these observations as well as this new design philosophy based on the formations and performance?
As you know, this field is always evolving. The new textbook by Kramer and Stewart is a major step forward because Kramer's book was great in 1996, but the field just rapidly evolved because we learned from these earthquakes. And we've had so many earthquakes that we have learned from that you'll see that the thickness of that book and the sophistication of the methods in that book have taken a significant advancement in the last 30 years. And so I think there's many good things in there, but that book, and John's in your Professor Stewart's in your areas, you can talk to him about it. That book was kind of completed maybe about a year or two ago and then going through the final stages of it. So it's a 2025 book based on probably 2023 knowledge. There's new things coming out all the time. So one has to always read that book and other books like that, but then they need to pay attention to the literature and bring new methods in because we're always adding insights and we want to attack problems with multiple methods. There's too much scientific epistemic uncertainty to just say my method's correct. And then also too, by focusing on the effects of earthquakes, like the effects of liquefaction, as opposed to did liquefaction trigger or not? Or is it cyclic failure? Is it cyclic softening? Is it cyclic this? The ground built up pore pressure, it softened, and that had an effect on the structure. You call it whatever you want. It's the effects of that phenomenon that matter the most.
That's good. Thank you very much, John. One more question. Yes, please, Gerardo.
Thank you for your presentation, Professor Bray. I wanted to ask you, during your visit to Turkey in 2023, what is your assessment in terms of the cause of the tremendous damage to hundreds of thousands of buildings? Is it bad? Was it fundamentally bad construction practices? Was it lack of engineering supervision? Or it's simply a failure of the code to take into account near fault effects?
It could be all of the above. And I will defer to a structural engineer who spent a lot of time on this, but I know enough that I've collected some information where there was corruption. There were cases where buildings were not designed well, some of the geotechnical issues, but then there were buildings that were overwhelmed because the forward directivity, in fact, maybe Professor Stewart will talk about that, that's one of the key lessons. They had a number of strong motion stations right along the trace of that fault. And it's an incredible database to learn from in terms of forward directivity. And I did see forward directivity effects in the southern part on bridges that were still standing, seeing the kind of lurching movements and things that you'd expect from forward directivity. Turkey, like the United States and Mexico, is a complex group, a society that has brilliant engineers, but they also have societal pressures sometimes, and there are things that don't get done by the building code, and we need to work against that. Obviously, a good building code that's well enforced is critical. Peer review of designs. It's amazing how human beings want to do the right thing, but when they know someone's going to be checking to do the right thing, they do a better job or a more conscientious job. I mean, the Seismic Mapping Act that was put in California, besides requiring investigations, which should have been done a long time ago, having the peer review just elevates the practice. We all work better when we have collaboration and challenges, as your introduction talked about. It's through debate and polite professional discussions that we all learn.
Thank you, John. That was a great answer. And again, the technical discussions and questions are needed in order to become a better engineers and do better designs. So with that in mind, please, Manika, do you have a question?
Thank you very much for the nice presentation. You mentioned a couple of terms of different classifications of liquefaction. So most of the damage that you show is related to cyclic mobility. No? We will say that. In all the terms, because there are different definitions by different authors, we might say, I don't know if you agree, that we can divide it more or less cyclic mobility and flow liquefaction or static liquefaction. But in my opinion, these two phenomena are not very different from each other. So it's not that there is a different soil or a different state. It's more or less, in my opinion, related just by the fact that the deviatoric stress in flow liquefaction is higher than the critical state strength, and cyclic mobility is lower than the critical state. So at the end, we don't have this sudden loss of strength for flow liquefaction. So with that in mind, do you think, because these two things are analyzed in a very different frameworks and very different ways, in that sense, do you think that we should be working more, trying to unify these two seemingly different but very similar phenomena, or is okay to go in two different completely directions to assess this phenomena?
Words should not be obstacles. The late Professor Harry Seed, when I took his course, said there's cyclic mobility with unlimited strain potential, and there's cyclic mobility with limited strain potential. And I think it's important to divide that, whether it's static or cyclic, into those terms. And I like to shorten things and really emphasize it. So I talk about flow liquefaction for low penetration resistances, because that's where the strain goes from very little to a lot. You're falling off a cliff, and you won't necessarily get a flow unless you have the static shear stress greater than the strength, but it could. So it reminds you that a factor of safety of 1.2 in that region is not as safe as a factor of safety 1.2 when you're in the higher penetration resistance where you have cyclic mobility. But then tying together static liquefaction and cyclic liquefaction, I always remind myself that the first quarter cycle of a cyclic simple shear test is a monotonic simple shear test. And you're right. I mean, if you're close to the phase transformation line or the collapse line, whatever you call it, you can get that to occur during that first quarter cycle, or it could happen during a monotonic loading. It's a fragile structure that rapidly builds up pore pressure, and then you basically head down toward the origin, and you might eventually in the lab hold yourself together and hit the phase transformation line and come back a bit. But in the field, you break apart and you get a flow liquefaction. We need to have unified terms. And maybe going back, one of the great contributions that the late Professor Juan Pestana made was the unified soil model. He was asked to develop a model for sand. And he said, why? Why not all soils? What's the magic of the number 4 sieve between a fine gravel and a coarse sand? And what's the difference between a silty sand and a sand and let's go into clays? And so one of the legacies of Professor Pestana is going to be this unified model. And I think we need to be more unified as we look at these phenomenon.
Thank you, John. One more question before we move to the next presentation. Jorge? No? The students? Thank you very much, John, for this great overview and for having the time to actually be here with us today. That it's a really sad day because of Professor Pestana just passed away, our friend. So, yeah, thank you very much. We're going to be moving to the next presentation, John. So
Very much. I really appreciate your time. And again, I apologize for not being able to be there.
thank you, John. So the next presentation is going to be about the current ground motion prediction models using Mexico City. The idea is that we have the ground motions, we have the soil, and we have the structures guy, and we want to see how the resilience can actually be achieved by looking at each of these parts independently. Please, Professor Mario Ordaz and Eduardo Reynoso, could you come here to the podium? Thank you.
Thank you very much. Good morning, everyone. So I will be explaining two things, I think. One is a sort of history of the development of ground motion prediction models in Mexico since the old times, and how they have evolved with the years, ending with the ones that we are currently using for the different things that these models are used, like probabilistic seismic hazard assessment and building code drafting. So this presentation was prepared by myself, Dr. Reynoso, who is here, and Dr. Dani Arroyo, who could not be here because of medical reasons. And I will be presenting, I will be delivering all the presentation. Okay, so these are the main topics that I will be talking about. So just a few things about seismic instrumentation in Mexico, how it has evolved, and then to remember some of the early models of GMPs before the 1985 Michoacan earthquake. These are very interesting models because they are really very early. So they go back, in some cases, to the 1960s. Then some models that came after the 1985 Michoacan earthquakes, but which are not used anymore. Then current models that we are using for normal faulting intraslab earthquakes, current models we are using for thrust interface earthquakes. Then we will shift to some detailed analysis for Mexico City, normal faulting earthquakes and thrust faulting earthquakes just for Mexico City. Then a brief mention of what we have done for the crustal local earthquakes, that they have become quite famous in the last years. So we are starting, I think, to analyze them. And then some remarks or some reflections about some of the characteristics of the seismic response in Mexico City that have to be had in mind when developing the models for predicting the ground motion. Then conclusions. So talking about seismic instrumentation in Mexico, and I will basically talk about the strong motion instrumentation in Mexico, so not necessarily the seismological instrumentation. So Mexico was one of the first countries in gathering the International Seismological Association, which was founded to advance the seismic instrumentation worldwide. So the first station that was put in operation in Mexico was a seismometer in 1910 in the observatory of Tacubaya, which now belongs to the university. And I think at that time it did not belong to the university. So then the first accelerometric station in Mexico City was installed here at the University City I think in 1960 or 1962. It was, or 1964. And it's, we think, the beginning of modern seismic instrumentation in the country. The station is just outside this building, or closer to the buildings of geotechnics. So if you have a curiosity, you can visit this venerable station. And now, when the September 1985 took place, there were relatively few instruments in Mexico City. I think there were 10 or 11 ground motion instruments in Mexico City. And, but the Guerrero accelerometric array had just been inaugurated, had just been put in operation. So the Guerrero array recorded the earthquake, and it was, if I'm not mistaken, the first time in history that a magnitude 8 earthquake was recorded so close to the hypocenter. Now, and after that, after the 1985 earthquake, about 100 seismic stations or ground motion stations were installed in Mexico City, and some other stations across the country. And now in Mexico City, we have a total of, I think, 120 stations operating and giving us very useful information for many things. So now, let me go to what I call the early models of ground motion prediction equations. The first one that I have here is one which was very famous at the time, is the Esteban Villaverde ground motion prediction model. It was made in 1973, and it was used. It included records just from Mexican earthquakes. Now, but then after drafting this slide, I remembered that there's an even earlier model, which was a model by Esteban Rosenbluth, which came out in 1964. And that's the model that was used in the 1967 paper by Esteban, in which he proposed the PSHA. It's a paper in 1967, and that model by Esteban Rosenbluth is one that was used in that paper, and it's a pity that I forgot that and I didn't put it in the slide, but there's a 1964 model by Esteban Rosenbluth. Then, and this model was made just for AMAX and VMAX, so PGA and PGV. That was more or less the state of the art at that time. Then, in 1984, Mario Bufaliza made as a master's thesis here, I don't know if maybe at the Institute of Geophysics or maybe here, right? He made a new ground motion prediction model, still for PGA and PGV, also based exclusively on Mexican seismic records. And then, well, it's interesting. These two models and also the 1964 Esteban Rosenbluth model start to have the shape or the general shape of the attenuation models that would be developed in the next in the following 10 or 20 years, I think. Now, that was more or less the state of things in 1985. But then the 1985 earthquake came, and things changed very fast. There were many models, or several models, which started to be developed. One by Professor Singh of the Institute of Geophysics and his co-workers in 1987 was still the old style, the old school, so AMAX and PGA and PGV. But in this case, it was using exclusively data recorded here at the university city. So this is the first time in the history of the Mexican ground motion prediction models that a single station model was built, and it was built for the station of University City, mainly for the reason that the station had been in operation since 1960 something. So it was the station in the country that had recorded more earthquakes. And also, perhaps the main reason is that it was a Mexico City earthquake, and then they were trying to study with much more detail what had happened in 1985 in Mexico City. Then there was another interesting model by Raúl Castro and others, which was a model constructed still for the university city, but based on the Fourier spectrum. So it was what was called at that time an attenuation model. It's a ground motion prediction model, but was not targeting PGA and PGV, but it was targeting the Fourier spectrum at the university city. And this model marked what was the tendency, or what was the school in Mexico of creating ground motion prediction models. For many years, basically all the models that were constructed were made initially for the Fourier spectrum, and then converted into response spectrum or other measures of ground motion through random vibration theory. Now, but it's interesting that starting with the model of Castro and others in 1988, and for many years, and back to that now, presently, we will get to that, the models have been constructed initially for the Fourier spectrum. And as we will see later, that marks a difference to the school of thought that has been followed in other countries, in other communities. But it also has more advantages that we will discuss later. Now, those were models for Mexico City, for the university city station. But then some other models were started being constructed using the recordings of the instruments, the new instruments and the instruments that were being deployed at the time. And one of them, which was, I think, very interesting, especially because this was part of my PhD thesis, it's a model by Singh et al., and I am in those al, which was, again, for the Fourier spectrum, but included a term, a finite source term, So, and the basic effect of including a finite source term is that the model predicted a saturation of peak ground acceleration and short period spectral ordinates with magnitude, And the reason is relatively simple to understand. If you have a fault which grows a lot with magnitude, then the contribution of the far edges of the fault start to be smaller and smaller, and that means that the high frequency does not grow as fast as it grew for the smaller magnitudes, and at some point it just doesn't grow anymore because of the an elastic attenuation and the distance of the to the faraway tips of the fault, right? So that and this model, so it was a kind. It's as you can maybe you can see here. It's similar to the to Bohr's model in the Fourier spectrum. So it has attenuation with distance. It has Q, etc. All the terms, but it has a source term which is different. Predicts saturation of peak ground acceleration, and it goes. If the distance to the fault is very large, then it collapses into a point source. No, so it's a nice model that goes slowly from finite source to point source. No, as distance grows, and this was a base for calibrating all the coefficients that you can see there. So the Q values and the kappa values, etc. Some parameters. This model was the base for the ground motion prediction model that was used for many years in PSHA for this type of earthquakes in Mexico. And as I mentioned, it started as a Fourier spectrum ground motion prediction model, which was converted into a response spectrum with random vibration theory, which requires knowledge of the duration. So all of these models were accompanied by equations to compute the duration of the intense part of the earthquake, which is required to go from the Fourier domain to the response spectral domain. Then in 1992, there was another model that was constructed, and the model itself was not very used, so it was not a great success, I think. But some of the observations that came in this paper and with this development were very important and still are very important, I think, to understand the ground motion in Mexico City, around Mexico City, and in other parts of the country. So the shape of the model was pretty standard. It's again for the Fourier spectrum. There's a constant. There's a magnitude term. There's a distance term, and then there's an elastic term. It's pretty standard, and so it was built for using recordings of in Mexico in several parts, but just rock stations, no, not soft stations, just rock stations. And I want to remark that because you will be surprised when you see the following graphs, because all of these are rock stations. So what we are seeing here is different frames are for different frequencies. So we go from 0.2 hertz, 0.4, 0.6, up to 5 hertz. And what we are seeing is the attenuation of, with distance, of a normalized measure of the ground motion. So the normalization is the amplitude of the motion normalized by the magnitude term of the attenuation relation. No? So what we see here is that the smooth lines are the 16th, 50th, and 84th percentile of the predictions of the ground motion model. So you can see that say for these frequencies, the attenuation looks reasonable. I mean, it's what you would expect. So the amplitude decreases with distance. But there are several stations here, rock stations, which are highly amplified. No? You see the same for 0.4 hertz, 0.6, 2 hertz. Well, this is 0.3, 0.5, 1 hertz, and you don't see it anymore for 5 hertz, right? Now, what's happening here? So some of these stations all of them are rock. So this amplification is not due to side effects. No, there are no soft clays, etc. stations there. This amplification this amplification looks like this. Now I'm plotting here the ratio between for a given station, the ratio between the observation and what would have been observed at the mean level of the attenuation model. So it looks like this. So these are amplifications of factor of 20, 30. These are for a single station as a function of frequency. So you can see some of these stations are inside the Valley of Mexico. So this is Tacubaya. This is University City. This is a station in the hills, which is called B74, some other stations. And then this is a station outside the Valley of Mexico, which is Cuernavaca. And this is a station outside of the Valley of Mexico, which is Teacalco. So what we see is that there's something, perhaps the older Valley of Mexico, so the Valley of Mexico that existed before the valley was closed and then it was converted into a basin, which is now. And this is affecting the motion at stations inside the Valley of Mexico, but rock sites, but it's also affecting stations outside the Valley of Mexico, no? And this is the reason for the discontinuity that we see in the calculations for Mexico City, including side effects, and outside of Mexico City. This is the real reason. So the reason of the discontinuity is not side effects. Now, this has been observed, so the observations of this paper have been confirmed later for more observations, but I think we haven't actually understood what's going on, no? And what's the reason for this? It has to be something big, because the peak amplifications are taking place in low frequencies, so this has to be something big. So this is the reason for the discontinuity, and what we have done when we are analyzing, what we are computing PSHA for the whole country, is to do, we don't have enough information to know which part of this, which portion of the central part of Mexico is subjected to these amplifications. So what we have done is to do a sort of merge between inside the Valley of Mexico and outside the Valley of Mexico, but this merge, it's very uncertain. So it's not, we don't know very well what to do. Which is true, what is true is that if you use a general model of attenuation and compute the motion for these stations, for instance, Cuernavaca and Teacalco, you wouldn't see this amplification. If you treat those stations as rock stations, you would see something like in this level, but you wouldn't see something in this level. So this amplification is missing in all the models that we have seen that pretend to be general for inside and outside the Valley of Mexico. Now, let me see. This one is also, this is the previous model was just for thrust events, right? But then Singh and his co-workers constructed a model for normal faulting earthquakes in University City, no? So, but just normal faulting events. So events that take place in the subducted slab. And it was type of the approach of Bohr. So it's a point source omega square model with coefficients that were calibrated and some amplification factors that were calibrated to match the spectra, the Fourier spectra that had been observed at that time at the University City coming from normal faulting events. So there was specific study for normal faulting hitting University City. And it was, as I mentioned, a Bohr type of model, or and the duration was computed using Hermann's formula. Now, there was another model, which was also part of my thesis, so it's an old one. It's a model for the Fourier spectrum at University City, but this had the difference, or the interesting thing, that it was a Bayesian model. No, so in this approach, you start these are the coefficients. So you see that the shape of the model is pretty standard. So a constant, a magnitude term, a distance term, and then an elastic attenuation term. So the model is pretty standard. But you start the model with a prior value, which comes from science or similar regions, etc. So you start with a prior value for each one of the coefficients. For instance, one that it's relatively easy to see, this alpha 2. So you start with a prior value of minus 0.5, which corresponds to attenuation of surface waves. No? So you say, well, you are going to have attenuation like surface waves, so this coefficient has to be minus 0.5 as a prior value. And you have prior values for the different parameters, including sigma, the standard deviation. And these parameters are updated through the Bayes theorem to get new parameters that include the prior knowledge plus the data. And this is, I think, a very reasonable way to construct ground motion prediction models. And one practical thing is that, you know, all of you that have constructed ground motion prediction models know that in most cases they are quite unstable, because the model cannot decide which term is to blame for something. So the Bayesian, the inclusion of Bayesian information stabilizes the results. No, so this model was developed in 1994, and then it has predictions for. These are the predictions of the model. It's in the Fourier domain. At that time, we were still using north-south and east-west components separately. So this model was constructed in 1994, and then it was updated some years later. These are the predictions for different combinations of magnitude and distance. This is for a fixed magnitude and different distances. We are not interested in short distances, because this is made for thrust events hitting Mexico City. So there are no events closer than, say, 200 kilometers. And again, University City, Fourier, that goes into spectral response using random vibration theory. No. Okay, so this was for the University City. So what we have used as a reference station in the analysis of the ground motion. And then we will be moving into the methods we have used for trying to predict the motion at subsoils in Mexico City. So the general approach is the following. We estimate first ground motion parameters. It could be the Fourier amplitude spectrum or the response spectrum at a reference station, this university city. And then we determine amplification functions in the Fourier or in the response spectral domains between instrumented sites, which are about 100 or 120, and the reference station. These are amplification functions which can be in the Fourier domain or in the response spectral domain. And then we estimate ground motion at instrumented sites using these amplification functions. No? So we compute for the reference station, multiply by the amplification factors, and then compute the motion at instrumented sites, and then interpolate the ground motion for arbitrary locations based on site characteristics and some spatial trends that I will describe. It's not a free interpolation. It has some interesting things that I will mention. Well, the ground motion at the beginning, the ground motion at the university city was made with the Bayesian approach that I described. But there were other efforts. For instance, using more or less the same data at that time, Reyes did a ground motion prediction model now for the response spectrum for University City, and also Miguel Jaimes did one in 2005 for the response spectra at University City. This is one example of the observed value in the September 14, 1995 event recorded in University City, and observation and computation. This is another example for the March 14, 1979, magnitude 7.6, observed and computed. So these are, again, single station models for the response spectrum. Well, some words about the amplification factors in this case in the response spectral domain. So what we see is that the ratios between what you observe in an instrumented site and what you observe at University City are pretty constant from earthquake to earthquake. And in many cases, they are similar to the 1D response, but not all cases, not in all cases. And this is, I think, critical. I will go back to that. So you can see, it's not clear here, but the ratios are pretty constant with some exceptions. The exceptions is that main exceptions are when the predominant period of the soil at that particular site has changed. No, as you know, the predominant periods of the sites in Mexico City are changing due to water pumping. So the soil is getting dry, and the mechanical properties are changing. So the period changes, no? In some cases, a lot. For instance, in the case of the SCT station, the period has moved from 2 seconds to 1.4 seconds or 1.5 seconds since 1985 up to now. It's a lot, no? So the spectral ratio changes because the predominant period changes. But if one normalizes the spectral ratios with respect to the predominant period at the moment that the earthquake took place, then the spectral ratios become, again, very constant, no? And we are using that observations to do the prediction of the motion in in the instrumented sites. Well, this is more or less the same. These are some examples of the spectral ratios in different parts of the city. You can see that there are some stations in which the amplification is huge. Some of them, the amplification is not a lot. And of course, in University City, the amplification is 1 because the ratios are computed with respect to University City. Now, and what I was mentioning, in many cases, these are similar to the 1D response, except at points which are close to the edges of the valley, so close to the edges of the firm ground. In those cases, the 1D modeling is not good, and using the empirical spectral ratios is much better than 1D modeling. Well, as I was mentioning, together with the prediction of the Fourier spectrum, one has to do equations to predict the duration of the motion. This is an early one by Stefan Rosenbluth, 1964. This one came in the same paper of the early attenuation model. And this is the equation they used for the duration. So this is the magnitude and this is the distance. It's interesting, it's 1964, so it's 60 years ago. This is essentially Hermann's formula with with coefficients that are a little bit different, but the components are essentially Hermann's formula. No, so you can see here an expression related to the corner frequency, etc., and a term that depends on the magnitude. Hermann's formula is from 1985, so this is 20 years before that. Now, after analyzing a lot of information from the recordings obtained in Mexico City, Reynoso and myself made another formula, a new formula to compute the duration, which is more complex and fits a little bit better the observed durations, and it includes a term that depends on the predominant period of the site. No, so the longer, in general, the longer the predominant period of the site, the longer the duration. In theory, this approach allows us to compute reasonably well the motion at instrumented sites, but then one has to compute the motion for other sites which are not instrumented. And then we are using a method which was devised and coded, etc., by Luis Eduardo Pérez Rocha in his PhD thesis, which is again a kind of is a form of Bayesian interpolation. So we interpolate the spectral ratios, but not the spectral ratios themselves, but the spectral ratios normalized with respect to the predominant grand period of the motion. You cannot interpolate the spectral ratios, because if you have one spectral ratio picked at 1 second, say, no, and another spectral ratio picked at 2 seconds, if you interpolate them raw at the middle, you would end up with a spectral ratio which has 2 peaks, one at 1 second and one at 2 seconds, and that doesn't make sense. So what we do is that we interpolate the spectral ratios normalized with respect to the predominant period at the time that the earthquake took place. I remember that the period is changing, and that has to be accounted for. Changes are huge in some parts of the country, of the city. And then once they have been interpolated with this Bayesian scheme, they are renormalized with respect to the predominant period of the site for which the computation is being made, okay? So you end up with a spectral ratio which is picked at the predominant period, as it should be, and it has the influence of the amplitudes of the normalized spectral ratios in other surrounding sites. Of course, in his thesis, Luis Eduardo Pérez Rocha made different measures of the error that was induced with that, and that was made by removing points and then interpolating for those points and computing the differences between using or not using that point. And the results are satisfactory. And we have used this method with confidence ever since. And these two things, the Bayesian model for University City and the Bayesian interpolation scheme were the base for a program, a system which was called Z, program Z, that was made to compute response spectra for sites in Mexico City for different types of earthquakes. So this was a kind of generalized ground motion prediction model, because it was a program, but you could input characteristics of the earthquake, like magnitude, distance, type of faulting, etc., and it would give you response spectra at the site of the city where you had clicked. So it had an interface. You could click there. You could choose your earthquake, a historical earthquake, or you could postulate an earthquake, so put essentially magnitude and distance, and then compute. This is the historical earthquakes. And then you could choose your site and compute for that particular site different types of response spectra for different types of earthquakes. In this case, 5 different earthquakes, or 5% damping and ductility demand of 1. So elastic events. No? One of the beauties, I mean, just as a side mention, one of the beauties of using Fourier spectrum is that you can compute response spectrum for all dampings you want. So you cannot, you don't have to do an analysis for all the dampings, but you can compute for other dampings. No? You could, with this program, you could also make maps, so the distribution of ground motion and under different events, and how it would look. And so it was, in a way, this is a program made in the last century. So it's more than 25 years ago. But it was a base for what we are using now, the SACID that we are using now. No? Now, I will move to the models that we are, so we live behind the models that we used in the past, and then I move to the models we are using now for different ground motion predictions. So let's see the normal faulting events. So one of them was made by Garcia and others in 2005. It's a pretty standard ground motion prediction model for the response spectrum at different periods, starting with very short periods, and using more or less all the events that were available at that time, just for rock, no? And this was published in, and we have used it. I think we don't use it as we did in the past, but we are still using it after some corrections, because we noticed, and I think Miguel Jaimes also noticed, that it was giving too high values for the short periods or the high frequencies. So we're using still a modified form of this model. Then there's a newer one made by Miguel Jaimes in 2020. He extended the data set used by Garcia in 2005. He incorporated new seismic records, and in particular, he incorporated the recordings from the 7.1 and 8.1 events of 2017. So it was a significant addition. The results are, in some cases, not very different to what we had with Garcia, except I think in some periods in which it improved the results of the 2005 event. I think this is in talking about ground motion models for normal faulting events. This is the newest model we have, the 2020 model. Now let's move to the interface events. No, not for Mexico City, but in general for sites outside Mexico City. So there's a model made by Arroyo and others, Dani Arroyo, the other author of this presentation, but he couldn't be here. So this is made for the response spectrum with more or less all the data that were available at that time. But the interesting thing of this model is that it's a Bayesian model. No, so it's a more complex. Form. So it has a form that resembles more the more modern ground motion prediction models, but the coefficients were fixed and determined using a Bayesian approach similar to the one I described, more complex because of the greater complexity of the model itself. So this is the model that we used since between 2010 and 2022, I think, when we went back to Fourier spectral models, and we changed with another one that I will show. Now let's go to models for normal faulting intraslab earthquakes, but not for Mexico City. So models like for 2017 event, or the 1980 or 1964, 1973, etc. All the normal faulting events that have hit Mexico City. So this is a model which is it's for the Fourier amplitude spectrum. It has a relatively conventional form, so it's a magnitude term. This is a distance term, which is body waves for shorter distance and surface waves for longer distances. But the interesting thing is that it has an azimuth-dependent and elastic value. So the direction, so the azimuth from the site to from the epicenter to the site matters, no? And it also has an attached formula to compute the duration, which has a magnitude-dependent term, a distance term, and a term that depends on the period, in the predominant period of the site. No? So the kind of innovation that this model has is that this azimuth-dependent and elastic coefficients. No? It's interesting because I think we have not explored fully this dependence of anelastic values with azimuth, etc. But we have examples of some propagation paths in Mexico that cross the wedge of the mantle. No, so that came out when we were doing the reanalysis of the Laguna Verde nuclear power plant. So it's clear that one would have to include some more complex terms here in the anelastic attenuation to account for some trajectories. In the case of the power plant, very relevant for the power plant, in which the waves cross the wedge of the mantle. No? So I think that this would have to be elaborated much more with better data. Now, these are some examples for some predictions of the model for two in the 2017 earthquake for two very important stations in Mexico City. So we have here the observed event, the observed response spectrum, which is the continuous blue line. Then we have the prediction by Contreras et al. Model that we will hear about in the following presentation. So this is Contreras, and this is the prediction of the model I just described. No. So this is for the university city, and this is for SCT station. No, so you can see this in the case of the firm ground. I'm now showing it in arithmetic scale. In the case of firm ground, it looks so both estimations look, I think, more or less reasonable with respect to the observed. In the case of the subsoils, the prediction by the way I have described is much better than the one of the model by Contreras et al. No? Now let's move to current models for thrust interface earthquakes. So this is the newest one. It was published in 2024. So it's again for Mexico City, thrust events, Fourier spectrum, magnitude term, distant term, and path-dependent anelastic attenuation. I said azimuth dependent. No, I was wrong. It's path-dependent. It actually does not depend on the azimuth itself, but on the path followed by the waves, and so it has an elastic terms that are path dependent, and again these Fourier spectra are converted into response spectra with random variation theory, and then we have a formula here to go from to compute the duration, which is needed by random variation theory. We have again now for the 1985 event, the observed value, which is the blue thin line. No, yeah, the prediction by the Arroyo 24 model, and then this is the prediction by Contreras model in University City and in SCT station. No? The same in arithmetic scale. So the prediction it's reasonable here, and it's quite good in SCT for the 1985 event. Now I'm approaching the end, and I will like to talk a little bit about local earthquakes. No, so local earthquakes You know that in recent years, we've had several local earthquakes that have induced very large accelerations in the Valley of Mexico, no? Actually, the largest peak acceleration recorded in history in Mexico City came from I think, magnitude 3.2 event that took place with a very shallow hypocenter, maybe 800 meters, and just beneath a cemetery, no? So damages were limited. There were no living people in the cemetery, and the event was felt. It didn't produce damages that we know, but the peak ground acceleration was, I think, 0.3 G, no? Which is larger than all the other values of peak ground acceleration recorded, even in subsoils in Mexico, no? So there has been interest in analyzing our ability to predict the motion with these events. This is an attempt by Dr. Singh to construct, again, a Bohr type of model with delta sigma, with some values of parameters adjusted to reproduce the observations, no? But this analysis has proved to be very difficult, no? Because to begin with, to locate these earthquakes is very difficult. No, the structure of the Earth at this scale is not very well known, etc. So the analysis has proven to be very difficult, and I think this is an open topic. Professor Leonardo Ramirez has been working a lot on this, and well, there's a model, but we have used it with a grain of salt, or maybe a kilo of salt, because we are not very sure about the quality of this analysis. No, it is, but we are several people and several groups are working on this, because we would like to have a reasonable estimation of the hazard that is associated to these earthquakes. No. Now let me go into how I'm doing. 15 minutes. Okay. First thing I would like to discuss is the nonlinearity of the response of the soils in Mexico City. Now, now let me see. Okay. So, well, the clays in Mexico City are known to have a wider elastic range, no? But of course, nobody thinks that is infinitely wide. So it should be entering into nonlinear behavior at some point. No, the problem is that and the findings by Contreras and Professor Stewart with the model of 2025 indicate or give some indications of the effects of or the size of the nonlinearity that could be expected in different parts of the city at different frequency values, etc. No, and this information comes from empirical analysis of the recordings obtained. No, but we are not convinced yet that that we are able to model correctly the nonlinear behavior of the soils in Mexico City. So this is a test that was made with two earthquakes. One is the September 19, 2017 earthquake, which induced some large accelerations in some parts of the city. And but then we are comparing what we observed in this earthquake with another earthquake, which took place on December 7th, 2023, very similar to the 2017 event, almost same location, etc., just a different magnitude. Same distance, but a different magnitude. So one thing is that the azimuth effects, the path effects, etc., must be more or less the same. And we could more or less thrust that that the differences that we see in the amplification factors might be attributed to nonlinearity, because the 2023 event is much smaller than the 2017. If we measure it with PGA, it's 58 centimeters in 2017 and 9 or 10 centimeters per second square in the 2023. So we should see some differences, no? These are the spectral ratios of the earthquakes, of the two earthquakes with respect to University City in both earthquakes. So the blue is the 2017 and the reddish is the 2023. So you can see that the spectral ratios are very similar, no? There are some differences, there are some stations in which you can see, for instance, we see here that the blue goes to 10 and the red goes to 30. You can say, well, there are some non-linearity here. Well, no, 2023 is the small one, no? No, yeah, you could say, yeah, there's some non-linearity here. The big one has a smaller amplitude in the ratio than the small one. But then you go to the next station and you see that the spectral ratio is higher for the higher earthquake, so it's not clear. The events are, the spectral ratios are too similar, I think. So we are not yet convinced that we have reasonable means to predict this effect, no? Okay. Well, this is more or less what I said. But of course, there are some other works, including one of Professor Singh in 1988, in which they claim to have observed noticeable nonlinear effects in some stations, in particular the CDAO station, doing more or less the same analysis we did, spectral ratios. No, so we went back into this station does not exist anymore. It was retired in 2000, the year 2000. But we went back to the recordings, trying to see what could be happening. One thing that could be happening is that some of the recordings at the base station, with respect to which the spectral ratios are computed, are very poor quality. No, this is one of them. So they're very small. So we think that perhaps Singh et al. Saw these nonlinear effects because of the poor quality of their recordings. You know? Conclusion of this is that our perception so far is that we don't have yet good means to evaluate the effects of nonlinearity inside the Valley of Mexico. Now, there's another complication here that we are facing. Most of the modeling of nonlinear side effects that has been made in Mexico City has been made using standard methods, so propagation of vertically propagating S waves, no? But it seems that in many places and in certain ranges of frequency, we are not, so the larger part of the energy is not being conducted in surface, in body waves, in S waves, but in surface waves. There are some indications, I think, quite clear that what we are seeing is surface waves, no? That explains in part why the modeling of 1D modeling fails when we approach the edges of the valley and the edges of the hills, no? But then it also complicates things, because if what we are seeing is the lateral propagation of surface waves, then the methods of analysis of nonlinearity should be others, should be different, no? So, who knows? Okay, the other thing which is very important, I think, and cannot be neglected, is the fact that the properties of the soil have changed in many parts of the city, in the stations. So what you recorded in 1985 or in 1990 in one of the stations would not be recorded if the same event took place today, because the mechanical properties of the soil have changed. And that has to be taken into account when creating methods to predict the ground motion, no? If you don't take that into account, you might be predicting what would have happened in 1990, not today, no? Or a mix, who knows? So this is an effect. It's a well-documented effect. It's an effect whose evolution is impossible to predict, because it depends on the particular pumping rates that are applied in the vicinity of the station, no? So it's essentially unpredictable. And but this is an effect that has to be taken into account when analyzing data. So somehow the data have to be normalized, corrected, etc., accounting for the year or the ages in which they were collected. And it has to be accounted for also, which we have done in the SACID methods. It has to be accounted for also when you are drafting design spectra. Because if you are drafting design spectra, you are not interested only in the shape of the motion, of the shape that the motion will have tomorrow, no? But you are interested also in the shape of the motion that the motion will have in 10 years, or 20, or 30, or 50. I just said that this is unpredictable, and it's true. But we have made efforts to predict, or to imagine at least some scenarios of possible evolution of this phenomenon. And we have taken conservative decisions about the design spectra, no? It's maybe counterintuitive, but if the soil is getting stiffer, some of the structures that are designed today might be in a worse shape in 10 years, no? You would say, well, if the soil is stiffer, that's good. It's good for some structures and it's bad for some other structures, no? So these effects have to be taken into account for deriving ground motion models and for the drafting design spectra. Well, now another thing that we have done, and I think I'm not sure that I have read all the literature at this respect, but I think this might be one of the few cases in which this kind of analysis has been made. So we took so we have a PSHA model for Mexico City. So we have the different ground motion models, all of them in Fourier domain. They all use the same application factors in the Fourier domain, et cetera, et cetera. We have an earthquake occurrence model. So we can compute PSHA for Mexico City at different stations, because we have the response of the stations and so on. But also, since the stations have been operating more or less constantly since 1988, most of them. So we have now, say, 35 years of recordings in all the stations. So we can compute empirical PSHA, empirical exceedance rates. And that's what we did here. So the blue ones, the smooth ones, are the PSHA results using the ground motion models and the earthquake occurrence models, and the reddish. What's the name of this color? It's magenta. Could be. Are the empirical exceedance rates. So if we had, and of course we cannot rely very much on the tails of these curves, because the tails are very sensitive to. So the last point of the magenta curve relies on one observation, no? So don't look at the tails. Look at the initial part of the curves. But if we had very wrong attenuation models or very wrong earthquake occurrence models, these curves would be very different. And they are not. No, they are curves for different stations at different periods. There are of course some differences. There are periods and stations which are better. For which the results match better. Some of them don't match so well. There are some more stations. So you can see the differences. In general, I would say that the comparison is reasonably satisfactory, which is not an absolute proof that the PSHA is correct. No, in these cases, there's not an absolute proof of that, but it's encouraging, because if the differences were very large and very extended in all periods and all cities and all stations, then we would know that there's something very, very wrong with the analysis. And our perception is that there are things, of course, that need to be explained, but we think that the approach is not very, very wrong. No, that there are things to correct, things that could be made better. But the general feeling after seeing these results is a good one. No, it's an encouraging one. These are different stations, different periods, so. Of course, this would have merited a more numerical analysis, etc. But these results are very new, so we haven't had the time to do that. Well, so I've tried to give you a panorama of the work that has been done in Mexico and for the country and for Mexico City since 1973, but in reality, I should have said since 1964, which is the date of the first Esteban Rosenbluth's ground motion prediction model. we have studied, or I have mentioned, we have seen ground motion models that are applicable across Mexico from normal events or thrust faulting events, and other group of methods and ground motion prediction models which are specific to Mexico City, which account for unique side effects and regional amplification effects. You know that now in Mexico City, as I have shown to you, regional amplification, not side effects, but regional amplification takes place even at firm site conditions, and these are on top of the well-documented amplification caused by clays, no, by the clays. So this is an interesting factor that I believe we don't understand well yet. No? We don't know the full spatial extent of this regional amplification. We have a more or less reasonable idea of the southern limit of the amplification, but we don't know very well where it ends through the north. You know, maybe the state of Hidalgo, who knows? And this is a problem, of course, of lack of instrumentation. No? And also, I would like to mention that we have these results of the PSHA for instrumented sites in Mexico City, which are reasonably good, I think, pending, of course, a more detailed analysis, which could give us indications of whether there are parts of the city in which the analysis is poorer, or frequency ranges in which the analysis is poorer, or a combination of both. But the general feeling at this moment is that the results are encouraging. I think this is not a very common study, not a very common way of trying to validate the results. It's at the same time a weak proof that the ground motion model models are reasonable, and that the earthquake occurrence model is also reasonable. But of course, it could happen that both of them are unreasonable, no? But the combination is reasonable. It could happen, not very likely. But so I think this was a good opportunity to show to you these results, which I think are encouraging, and well, that's it. Thank you very much.
Hello. Thank you, Mario, for your very extensive and insightful presentation. We have time for a couple of questions before we go to have some break. We're going to be coming back to these key issues in the technical discussion session later on today. But yeah, I would like to have a couple of questions right now, just to start open the floor. I don't know, someone has any question for the, yes, please, Laura.
Thank you, Mario. Because that's fine. Thank you, Mario, for the talk. It was very, very insightful. You mentioned about that we need instrumentation, and we're in the process now with the Seismological Service and the Institute of Physics to deploy and improve the network. What do you think would be best for the regional observations that you see, the amplification? Should we instrument more the Trans-Mexican volcanic belt? And for Mexico City, what should we instrument more? We have deployed last week, this week we deployed a borehole in nearby Miscuac, and we have a couple of deep borehole stations. Do we need to put more? What do you suggest for for proving or testing more of the ground motion models you have?
Yeah, thanks for the question, Leonardo. I think that some instrumentation for the regional amplification. I think some instrumentation would be needed in the north of the city, maybe reaching all the way to Querétaro. No, I think that that would be useful. Also, it would be useful to have input from geology. No, so maybe we should start partnering with someone at the Institute of Geology, or we had a geologist very much interested in that, but he passed away. No, Moser. It was, I think, natural that he passed away because he was 100. No, Gerardo, or 95, 95. Yeah. But I think that would also help. No. Now, in the case of Mexico City, my impression is that in the flat parts of the city, I think things are smooth. No, mm-hmm. So the predictions of the 1D are more or less reasonable. No, so at least they are reasonable to be used as priors for the Bayesian interpolation. But where we see a very strong variation and not very easy to understand is along the edges of the valley, the different edges. No? So the border with the hills at the west, mm-hmm. but also the borders of the hills, the Cerro de la Estrella, etc. No, so if I were to choose places to put instrumentation, I would choose lines or rings across but a very very short distances. No, 1 kilometer from the edges, something like that. Because my impression is that things there are not smooth. No, so the lateral interaction might be playing a very important role.
Thank you.
Thank you very much. Any other question? Actually, right here. Morgan, please.
Great, thank you. I enjoyed that talk a lot. Can you say a little more about what's known about deeper velocity structure in the area with the high regional amplifications? I mean, do you have thoughts of
I don't know enough.
What's giving rise? Okay.
I don't know enough. I couldn't. But we have some geophysicists here that... No. I thought you were going to ask about the ground motion prediction models in northwestern Mexico.
Are those the local earthquakes?
Are
those the local earthquakes? That was my second question. I was surprised by the very, very low stress parameter in that.
Yeah.
Those models. Do you have thoughts there?
Well, I think that I'm not sure that's a meaningful stress parameter. I think it's an artifact for fitting the spectra, no? But it's very fluky, because if the location is different, then everything changes, no? So since we don't have good locations, we don't have good magnitudes, everything is very fluky, no? So that's what we have now, but I'm sure that this is not the final result. This is just the beginning of the research on this.
Thank you very much. One more question here, Professor.
Mario, thank you very much for your talk. It was quite extended and nice. You say that your regional amplification were not successful. Maybe you are mistaken, because actually it was a great result to show that the reality of regional amplification beyond all doubts. Even if the structure, even if the spatial extent of the structure is not unknown, We did an experiment with Michel Campillo and instrumented just to Teotihuacan. And we think, without entering into details, that this is a product of the Mexican volcanic belt. And the amplification is because of the low strength of the volcanic rocks that are there. Are volcanic rocks overlying granitic structures, are a kind of, side effects, but of regional type. Is what we call firm ground, but still some amplification. With these results we did with Michel Campillo, Isri was also participating. So, and then I consider these results of Ordaz and Singh in 1982 was one, actually I will talk in my talk tomorrow as one of the cornerstones for the understanding the response of Mexico City. On the other hand, the good news of your results, recent results that showing that the PSA formulation is very robust and is a good news. We have to stress that this together with the region, the relative stability of the valley, regardless the origin of the earthquake, regardless the type of the earthquake, which is a puzzle for many people and for us in many aspects, is a good news that the SACID is a robust tool to give rational and trustworthy estimates of ground motion in the city. So it's worth to express congratulations to your work.
Thank you very much. No, I was saying that the model itself was not applied for a long time. No, we changed to different things. No, but the finding, I think, it was very important. No, and also I would say it was successful because for one reason or the other, I think this is my paper that has the largest number of citations.
Yes.
Yeah, I don't know why, but.
I don't know, Miguel, if we can have your question later. Then we can go to the coffee break, and we're going to have the discussion session talking about these issues again. And I invite everyone to stay to the discussion session. It's going to be really insightful. Thank you. Let's go to the coffee break. We will be here in 15 minutes.
Los reconocimientos hasta el final.
Sí, hasta el final. Sí. Vamos a continuar con el taller. We're going to continue with the workshop. The next speaker is Professor Jonathan Stewart. He's going to talk about Bio of Mexico's AI response for implementation in ground motion models. So, without further introduction, please, John.
Okay. I'm not sure I need the step here, but I'll take it. Well, let me start by thanking SMIS and SMIG and Presidents Pinto and Manica for hosting this event and the invitation to join you. I don't know if they're still here or not, but I appreciate their invitation. I appreciated the thorough review of ground motion models in Mexico and in Mexico City that we saw before the break. I consider those models, which I've looked at in the literature, but I think I learned new things about them from the presentation this morning. Those are defensible models. They fit the data, and they've been working for the seismic hazard analysis that you've been doing. I'm not up here to say you should not use those models. So if anybody thinks that's my message, then that's incorrect, okay? Rather, what I am here to do is to talk about an alternative way to do ground motion modeling, not necessarily to replace, but to supplement the ground motion modeling and the good work that has been done over the last few decades. The approach that I will be talking about is much more closely aligned with how this is done almost everywhere else in the world. I don't know of any other place in the world where you have one ground motion modeling approach for the entire country, except a carve out for one particular place. So that's a very unique feature that you have here in Mexico City. And as we learned this morning, there are reasons that that has been done that way. We heard from Dr. Bray, who spoke first, that it's a good thing. One of the things he mentioned is it's a good thing to approach problems with multiple methods. I'm quoting him there. Approach problems with multiple methods. And really what I'm talking about is an application of that concept. So let me see if I can advance the slides. So I am getting dings. Let me try going that way. Okay. So I want to acknowledge the research team that did the work I'll be talking about, Victor Contreras, who's listening online through the YouTube channel, and Dr. Mayoral and Dr. Perez Campos, both of whom are UNAM faculty. The work that I'll be talking about really builds off of the NGA subduction project, and so this slide is to introduce a few things about that project. The PI was Yusuf Bezorgnia. There's a group of people that worked on the database. You see the sponsors there. The earthquake spectra cover on the right is where the database and the models for that project were published, which was in 2022. So that project effectively ended in 2022, and for reasons that I'll talk about, we felt there was an opportunity to improve the models, particularly here in Central America and Mexico. And so that'll be what I'll be focusing on, but we are building off of NGA subduction. So the subject of my remarks here is really ground motion modeling, and when we talk about ground motion modeling, there's different scales that it can be done at. These NGA projects do look at the problem from a global perspective, and there's reasons that we do it that way. So the map on the right shows the global regions where subduction earthquakes have occurred and which produce data that went into that project. And by the way, GMM is just an alternative acronym. It means the same thing as GMPE, as in Professor Ordaz's presentation. When we have these global models, we customize them for particular regions that have data. And so we'll be talking about that regional customization for Central America and Mexico. And the map there shows the events that were considered in NGA subduction at the time that that project was done. Obviously, we're here in Mexico City, and the Valley of Mexico site response is actually in the title of my presentation. That's really the main focus. But in order for that to be in the proper context, I need to also talk about the broader issue of ground motion models for this region. And so the aim of all this is to provide ground motion models that can be used in PSHA, which produces the seismic force levels used in seismic design. So to do that, I'm going to go through these 6 items in the agenda. I'll have an introduction to the problem with a little more specifics about the different scales and the different attributes of ground motion models we like to see. We'll go through some GMM's overview connected with that. Then I'll go through the database, both for Mexico and Central America as a whole, and also for Mexico City. Then we'll get into the regionalization of the ground motion modeling for Mexico. So that would be the broader ground motion model for the entire region. And then we'll get into the Valley of Mexico site response. So there's a lot of different sections here, but about half the time will be that 5th bullet, the Valley of Mexico site response. And then we'll summarize. So in terms of GMM's overview, okay, so there's different terms that we use, and they imply things about the scale of the model. So ergodic is a term that is used when we are not doing things that are intended for specific application at a particular site. If they are applied to a particular site, there's a lot of uncertainty that goes with them. Okay, so these ergodic models can be done at a global scale. The last time that this was done, and this was the final product, was the NGA West 1 project, so that would not apply except for crustal earthquakes in Mexico. That was really intended for places like California, Taiwan, Japan, Turkey, and so on. We learned through that process that these global models had significant biases as they were applied in different regions, not really in California, but in other regions. And so as we moved on, we made some changes. Okay, but these ergodic models, they're using a very large global database, and they're representing the average conditions. So essentially, when you're predicting the ground motion in California, you're actually kind of averaging things between California, Turkey, Taiwan, Japan, and so on, to the extent that those different regions are represented in the database. Okay, so these ergodic models have certain features to them, and I'd like to just highlight some of the things we like to see in our ground motion models. So we're looking here at the natural log of a ground motion parameter y, given a certain distance, maybe 50 kilometers or something, and the horizontal axis is magnitude. So this is magnitude scaling. How does ground motion change with magnitude? Most global models are going to look like this. So you notice that there is a linear portion right here. Okay, so that is not accidental. First of all, the data supports it. But beyond that, the definition of magnitude, local magnitude or Richter magnitude going back to the 1930s, is the level of ground motion in log units for a certain distance from the source. So you're basically defining magnitude based on ground motion. So it stands to reason that the ground motion would increase as the magnitude increases in more or less a linear way. But that doesn't continue, it does saturate, okay? And Professor Ordaz talked a little bit about that. When you get to these very large distances, very large magnitudes, you're not seeing the parts of the extended fault that are very far away from your site. You're only seeing the part relatively close, which might as well be a smaller magnitude in terms of the portion of the slip that's controlling. So this is the kind of feature, I'll come back to this a few times, this linear and saturation that we will see in global models, because global models are going to cover a broad enough magnitude range to see it, and we don't always see in local models, because local models don't always have magnitudes going high enough to sample that. Another key part of these models has to do with how the ground motion changes with distance. So now we're conditioning on a given magnitude, say magnitude 7, and how do things change with distance? And we typically see something like this. So there is a saturation. This is a different kind of saturation. This is a distant saturation near the source, right up here. Then it gets to be roughly log linear, and then it attenuates down faster at very large distance. So there's kind of 3 components to the model: the part that controls the saturation, the geometric spreading right here, and anelastic attenuation at the larger distances. So these are all elements you'll find in a contemporary ground motion model. Now, these models, when we take them from a global area and we apply them to a particular region, may well have some bias. And that bias can take different forms, and we'll see some of that as we go forward. Recognizing that those biases exist, the NGA West 2 and the ongoing NGA West 3 projects are taking a different approach, and NGA Subduction did the same thing, because NGA Subduction followed NGA West 2. We had learned that lesson and we were applying it. So these NGA West 2, 3, and Subduction have global versions of the models, but they have regional adjustment factors. Now, a region, when I say a region, what I mean there is pretty broad regions like California or Central America and Mexico. Taiwan is another one, things like that. And when we look in those particular regions, we will see some differences sometimes. So we might see, for example, the ground motions on average are higher for a particular region. The breakpoint magnitude may be different in a particular region. Okay, so that could manifest in the source part of the model. One of the most common things we see, actually, is this variation in the anelastic attenuation. So the crustal structure is different in different parts of the globe, and we can see different rates of attenuation. Sometimes it's faster, like I've illustrated there. Sometimes it's less than the global model. Global model is, by definition, an average. And then there's site response. So in the NGA models, we use VS30 as the primary site parameter. We use other ones as well. And a typical pattern from a global model is you would have amplification here, log VS30 here. This is for a given period. There's typically modest change with VS30 for low values, a steep scaling interval, and then again modest at the higher velocities. So this is kind of a typical pattern looking globally, but then if we look at a particular region, we may see different scaling. So this has become a really big issue in the United States. We had from NGA West 1 and NGA West 2 a model that looked like this, and we were applying it everywhere. And then we looked more carefully in the central and eastern North America region, and we saw something that looks like the red line. The change of site response with VS30 is weaker, and that has to do, we think, with parameters other than VS30 having an unusually large influence there. And so we can see these different levels of scaling. So that's at kind of a regional scale. So now we go even finer. So we have the globe, we have regions like Central America and Mexico, and then we can have subregions that have a very particular condition that we need to deal with. Okay, and that's really, as we start to get into something like Mexico City, this could be a subregion where we have a variation off of the regional model to fit the observations there. So you might have something like this where the site amplification is just bigger, and that's basically what's going on in Mexico City. And we typically see that when you have a unique geological condition. We have things like this in California too. There's the California Delta region has very strong site response that just looks different than the rest of the state. So this isn't surprising when you see these sorts of features. And we can model them if we sub-regionalize the equations. So as I'll explain as we go through, really the keys, as we found looking at the data here in Mexico, are mainly two things. There's faster attenuation in the back arc, and I'll explain what I mean by that, than we would have in the overall regional model, or certainly in global models. And we have the well-known differences in site amplification here. So with that, I'm going to go to the database. Okay, so this slide has to do with the NGA subduction database and its attributes before we updated it for Central America and Mexico as part of the work that I'm focusing on here today. Okay, so in the NGA subduction database, it was released in 2019, so even though it was published in 2022, we're developing data up until 2019. We have a cutoff at that point, and then we basically focus on modeling. Actually, the cutoff was even a little bit earlier. That was the release of the data was in 2019. Now, in the Central America, Mexico area, we had a minimum magnitude that we considered of 6. That's a larger minimum magnitude than we have, for example, in the Pacific Northwest. And you might wonder, why would we do that? Well, it's actually very simple. Our funding was to develop a model that works globally, but our main focus was to make sure it worked in Cascadia. And so we were going to smaller magnitudes there. And frankly, we don't have large magnitudes there. The level we went down to in different parts of the world depended largely on the degree to which the data could be readily integrated into our workflow, the amount of effort that was going to be required to develop it, and given those constraints, we just couldn't deal with all the information below magnitude 6, and so we applied this magnitude 6 cutoff. We have, if you look at what we had in aggregate, we had 80 events with event type assignments, so that means we're assigning interface, slab, outer rise, or crustal, mostly interface or slab. The largest interface is the 1985 event that everybody here is very familiar with, and the largest slab was 1999. You don't see the 2017 and 18 earthquakes here. They occurred after the cutoff where we stopped gathering new data. So it was published in 2019, but that cutoff was actually in 2016. Okay, so I'm going to just cycle between these two maps here. This map is showing the earthquakes that are included in the database for NGA subduction. And this map is showing the earthquakes that were included in colors and the earthquakes that we had, and we actually had some ground motion processing for, but which we did not have all the metadata for. So it's a little bit complicated, but all these earthquakes, we had them in terms of the ground motions. We had not fine-tuned the processing of all the ground motions to the extent that we would have liked. It was more of an automated process. And we had not collected all the metadata for the white earthquakes. That was where the workflow essentially was such that we couldn't finish that. Okay, so we were missing all these small earthquakes, less than 6, prior to 2016. So in the present work, we tried to go back and fix that problem and also add the data for the large earthquakes in 17 and 18. So we start with that NGA subduction set of files, 2019 release, 2016 data cutoff. We added earthquakes, we added recordings, and we kind of revisited with the help of Professor Mayerl and Shirley Campos. We revisited all the site parameters. So there's 2 types of events. We looked at large events after 2016, and we looked at all the magnitude less than 6 events before 2016. As I mentioned, all the ground motions were in the database, but they were lacking metadata, which we filled in. So what I'll discuss here briefly is the added events, their source parameters, talk a little bit about the path parameters, talk about site parameters outside of Mexico. Is that my phone dinging like that? No, okay. And ground motion processing. Okay, so for those less than 6 earthquakes before 2016, we had moment tensors that we gathered from regional and global catalogs. So we have a certain protocol by which we assign the preferred moment tensor. So that would give you a location, a seismic moment, and a timing. One of the efforts that was a fair amount of work was these event type assignments. And so the workflow for that essentially involved plotting the earthquake relative to the USGS Slab 2 model. This is a model for the interface, and seeing where it falls. And in the case of the one shown here, it's basically on the interface. It's a reverse earthquake, so that would be assigned as an interface. You know, if you have earthquakes occurring up in this area, we're going to assign them as crustal, and if it's down in the subducting slab, we're going to call it a slab. We also do some simulations of the finite fault dimensions, not very important for less than 6 earthquakes, but it's part of our normal workflow, so we can measure distances to the finite fault, not just hypercentral distances. Okay, so this is where we end up in terms of the data set. The NGA subduction data set was all these ones in blue. This is magnitude, distance, space. The added less than 6 earthquakes are filling this in down here. And then this is the same plot, but now we're not distinguishing between the 2 phases of the data collection. These are just the different event types. So interface, slab, outer rise, and crustal. Okay, and this is the impact of that work on the number of recordings plotted as a function of time using the event year. So this is the event year here. This is interface and slab. This is what we had before, and this is where we ended up now. So we're approximately doubling the number of records that we have. Although I should say that many of those records were from events that have few recordings. So sometimes they end up getting screened out for model development. Then we have the 3 large magnitude events. So this was really the aspect of the data set that motivated us to do the work, is that we knew about these events because we were working up until 2022. We couldn't go and absorb this into our workflow given all the other things we were dealing with. So when we reached out to our colleagues here at UNAM, it was largely to make sure we captured these events and could learn from them. So I think you're all familiar with these in 8.3, 7.2, 7.2, and these are the finite faults that were selected for each of these earthquakes. So these are all finite fault models that are in the literature. We basically selected the preferred model. There are certain attributes we use to identify the model we prefer. We can take that up in QA later if you're interested. And then we do some trimming to get rid of zones with very low slip, and then we calculate distances from that. Okay, so that's what I just said. The other thing I'll mention on this slide is we were able to access ground motions from 5 different networks. They're identified here. So these are the acronyms for these networks, and some of them are in Mexico City only, and others are kind of spread throughout the region here. One of the things we did as part of this work with UNAM was, and this was, I think, motivated in part from discussions we had when I visited here in 2022, and we talked to some of the geologists and seismologists here, is we relocated the volcanic front that we had established at the time of NGA subduction. So what we had done at the time of NGA subduction, that's this red line here. We had this line which was basically connecting volcanoes, and the reason we have that line is the back arc is the region behind it, and the fore arc is the region in front of it. So that's what this is showing here. And as you'll see that these back arc and fore arc regions, these are examples of subregions that have different path properties. Well, we relocated that front from the red line to the purple line so that we were on the south end of the am I saying this right? Trans-Mexican volcanic belt. And that was an important thing to do that we think improved the model. We revisited all the site parameters in Mexico as part of this work as well. We looked really hard. We contacted people, but ultimately we actually found no shear wave velocity profiles outside of the Valley of Mexico. That's not to say they don't exist, it's just that we couldn't find them. So what we did is we estimated seismic velocities, or VS30, using surface geology and using a relationship between surface geology and VS30. The data processing, I won't spend time on this detail. I'll just say that with the data processing that was done, you start with the raw records, you do instrument correction, and then there's the filtering, baseline correction, intensity measure calculations, including response spectra, Fourier spectra, that follow standard NGA protocols that are pretty well documented. There's very careful attention given in that to identifying the lowest usable frequency or the longest usable period for the ground motion analysis. This just shows the distribution of PGA with distance by network, and it shows kind of where the data are for the different networks. This is for this 8.3 event. So we have PGA distance for each of these plots. The only difference between the plots is which stations are highlighted. So all the data is shown each time in gray, but in this case, the RAII UNAM network is highlighted in black. And you can see it's broadly distributed. Same with the IG network. And then the RACM and VM networks are, you see these vertical lines here indicating that they're in Mexico City. And so this is now the combined data set once we integrate not only the less than 6 earthquakes, but these 3 well-recorded earthquakes. And these really are extremely helpful earthquakes because they do occupy larger magnitudes, particularly this one is the largest. And they give us many recordings over a wide distance range. Not so many of the previous earthquakes had that feature, so that's very helpful. So all the data that we developed, there's the NGA subduction database, it's all publicly available. The added data, including the resampled site parameters, all publicly available. We are strong advocates of transparency, so everything that we've done after the checking that we did and everything is there at a DOI. Anybody can access it and do their own analysis with it. And we're happy for people to do that and find different things than we found. So let me go on now to the Mexico GMM regionalization. So this is not the Valley of Mexico yet. This is the overall regionalization for Central America and Mexico. And in order to discuss this, I need to talk about how we analyze the data to see the effects we're looking for. So it really starts with the calculation of total residuals. Let me walk you through that. So that's the data. So that could be, for example, PGA or 1 second spectral acceleration. Index I is an earthquake, earthquake I. Index J is a recording station. Okay, so that identifies a unique record. We subtract from the natural log of the data the prediction from a GMM. So that prediction includes a reference rock model, which includes the magnitude effects and the distance effects. That is from NGA sub. So we use several different models. Okay, we'll mostly talk about the Parker-Odell model. And then we add to that a site response in log units. Okay, so it's multiplicative in arithmetic units. So what do these residuals tell us? Okay, so we have the misfit between the observation and the model. What can we learn from that? So we can see if the data demonstrate bias. That would indicate if there is a systematic shift of the data relative to the model, that means that there is bias. If we see that the data, for example, trend with distance in a different way than the model would predict, that's a scaling error. Okay, so there's a scaling error and we can go in and make adjustments to fix the model. So we're really interested in both of those kinds of things. So those were total residuals. Then we do some partitioning. So some fancy statistics come in here. This is called mixed effects analysis that you can learn about in statistics classes. So the left side of this equation is that total residual. And we partition it into a mean bias. So what is the mean overall bias of that data relative to the model? We have what's called an event term that goes with the earthquake event I. And as I'll show you in a minute, it relates to how much the earthquake is systematically high or low. And we have a within event residual. Let me walk you through the meaning of these terms in a little more detail. So I'm plotting the natural log of ground motion versus distance with a model prediction, say for a magnitude 7 earthquake here. I may record the data for a particular earthquake, and I get the red dots. And you'll notice the red dots are higher than the model. If we were to fit an equation to that set of data, we would see that it's shifted up, and that upward shift is what we're calling an event term. The next earthquake with the same magnitude may well have a downward shift, okay, and be lower than the model, and that would have a negative event term. This is a totally normal and natural thing. We see it in earthquakes all over the world. Some earthquakes are higher than average, some earthquakes are lower than average. This is not a cause for concern. Doesn't mean the model in and of itself, just seeing a misfit of a single earthquake doesn't mean much, okay, because you can have these shifts through the event term, and it's important to separate those out in order to study path and side effects through the within event residuals. So having done that, we're going to ignore the event terms for a moment, and we're going to look at those within event residuals. And here what we're doing is we're looking at the within event residuals and how they vary with respect to distance, but only in the forearc, so on the south side of that boundary that we looked at earlier. And we have here the within event residual, distance, and 4 different parameters, PGA, PGV, and 2 different spectral periods. The data are shown with the red symbols, and the bin means are shown there. There's always going to be a little wobble up and down. What we're looking for is there a systematic trend where the trend with distance is incorrect? And we're not seeing that. Now, I should say that the model that was used here is one of the NGA subduction models before any regionalization. Okay, so just using the model as published. And so we're not seeing in the forearc a problem. When we go to the back arc, which had not been considered in this particular NGA subduction model, we need a way of representing how much of the path is occurring within the back arc. Okay, and so the equation here is a way of representing that. So you have this dimensionless factor, FB, it's the fraction of the path in the back arc. We multiply that by the overall rupture distance to get the rupture distance in the back arc, basically, that R rep B. So I'd like to illustrate those over here. This is a schematic of a subduction plate boundary. This happens to be one that I drew for the textbook for the Pacific Northwest, but the same principles apply here. If the volcanoes more or less identify the location separating forearc from back arc, we're looking at the back arc to the right side of that boundary. And if an earthquake occurs where those arrows are, we have rupture distance would be measured from the rupture surface to a site over there on the back arc, as shown. The R rup B that we're trying to characterize here is just the portion of the rupture distance occurring within the back arc. Okay, so we're trying to see what the impact of the back arc is on the attenuation. We have to look at the distance in that region. So that's what's being done here. We have the R rup B parameters. So 0 does not mean 0 distance. It just means you're right up against the volcanoes. Okay, and this is the within event residual again. We have the same 4 parameters, and we are seeing, there's a lot of scatter, but we are seeing a downward trend here in these plots. Not for the long periods, and not for PGV, but for the shorter periods, we see this. And so we're fitting that behavior with this equation right here, where this parameter right here is the slope of the line representing additional back arc attenuation. Okay, so that's something not in the NGA subduction models that we felt needed to be included. If we basically do those kinds of calculations across a wide range of spectral periods, separately for interface and slab earthquakes, we see this. So this is period, this is that slope parameter. When it's negative, and by the way, these are all times 10 to the minus 3, but when it's negative, it means that the attenuation is faster. So what you're seeing in Mexico is that you have a faster rate of attenuation on the back arc than you have on the forearc. This is important because Mexico City is in the back arc. Okay, so we have these different attenuation rates that are going to be important to consider. We looked at VS30 scaling, again, not for Mexico City at this stage, for the rest of the country. So we're going back to this equation for the within event residuals, but now we are partitioning that. So this is the within event residual. We're partitioning that residual in order to extract a site term. And that site term basically represents for site J, on average, how offset from the average of all the sites is it at a particular, say, spectral period. So that's a way that we can study site response. And we see these eta Sj terms have a lot of scatter, but they have a mean of 0. And they go up and down about over -1 to +1. If you look at the bin means of these, we don't see any trend. So what that means is that the VS30 scaling that was applied from the original NGA subduction model is working everywhere except, well, I haven't gotten to Mexico City, so that doesn't apply to there. I will just point out a couple of interesting features that we were intrigued by, but we couldn't do much with. So the colored blue symbol here, so these are recordings in Puebla, and you see them in all the different plots. And for most of these periods, it's higher than the average. So that's telling us that that recording in Puebla is not following the VS30 scaling model. It is bigger. And it would be interesting to do a more deeper dive into what's going on there. We just lack VS profiles and other information to allow us to do it. But it's an opportunity for further research for sure. Okay. And just to sort of round this out, we look at the event terms versus magnitude. These are standard plots. Again, we expect an individual earthquake can be high, it can be low. We're looking for trends. Is it sloping that way or is it sloping that way? And we're not seeing any systematic patterns here. So that suggests that the source model is working fine. And then there's the overall bias. Once you account for the back arc attenuation, you find the overall bias versus period is not 0. It's fluttering around. Sometimes it's nearly 0, negative, positive. These are the confidence intervals. And overall, it's hard to reject the original constant term, so we did not do so based on this. So the outcome of this is that the Parker et al. Model with the back arc adjustment is unbiased in the amplitude and source path and site scaling relationship. So that became the basis for the work we did downstream with the Valley of Mexico. Okay, so that brings us to this one. As I mentioned at the outset, this is where I'll spend the most time. And I'm going to break up the Valley of Mexico site response into these 4 sections here. So what is the data analysis we do to infer site response here? It's very similar to what I described. I'll just customize it a bit for this application. We'll talk about the site conditions here in the Valley of Mexico and the data we were able to collect. We'll talk about our site response model and the comparison of our model to current models. So this will be similar to what you saw from Professor Ordaz, but looking at a lot more sites. Okay, so let's start with how do we do this analysis. These are the total residuals again, so I won't go through all this. We have the partitioning, as I mentioned before. So we have the constant term, we have the event terms that we're just taking from the previous analysis, we have the site terms, and this is the remaining residual. Okay, so that site term is where we'll be spending most of our time here. So that site term, what it represents is the mean offset from an FV model, or an FV model is just a site response model. So then what we're going to do is we're going to take that site term and we're going to change it a little bit in order to find this site term, which is calculated relative to reference rock, which is 760 meters per second. That's kind of a standard reference condition globally that's used. So we take that site term and we add to it the prediction of the site response model. And essentially, because that site response model is referenced to 760, the addition of this makes it go to a 760 reference. And it's this eta SR. Think of that basically as site response relative to 760 that will be used for model development. Now, in terms of site conditions, what we're looking at on the right is a geologic map of the Valley of Mexico, or at least a portion of it. And on top of that map, Victor has plotted the ground motion sites that we're using. There's 89 of them, and the diamond here is different site measurements, and you can see where they line up and where they don't. We gathered 57 shear wave velocity profiles from literature, downhill methods, suspension logging, and different surface wave techniques. Most of those are not co-located with ground motion instruments, unfortunately. We gathered 50 site periods from HVSR measurements, so we have the full HVSR curve, or computed from VS profiles that have high impedance contrast, so you can calculate the site period. So we have 50, 28 of them come from HVSR and 22 from calculations from VS profiles. As the work evolved, we thought it would be helpful to look at a depth parameter, and the depth parameter that was practically obtainable, given the information we had, was the depth to a lower coarse grain layer, ZLGC. It comes from the reference you see there, which has a contour map of this depth that we could use. And ultimately, we're having to come up with these parameters, so VS30, site period, and ZLGC for 89 Valley of Mexico strong motion sites coming from those different networks that I described before. Okay, so there are zones that are used. I think you're all much more familiar with this than I am. These are used for site classification purposes for developing design ground motions. So here we have the map from NTCE, and superimposed on the map are the different ground motion stations and site measurements that we have. So what we did is we took the data we have on VS30 and site period, and we saw how that looks as a function of zone. Okay, so we have here zone 1. This is sort of the reference condition, like at the CU campus. This is transition zone, and these are different lake bed zones. Part 3 here, and what you see is that the VS30, so this is box and whisker plots. You may be familiar. This is the mean, the blue is the median, and this is just representing the spread of the data. So we see that the VS30 is decreasing as the zone number increases. When you get to these zones, particularly C and D, there's very little distinguishable difference. Not a big difference here either. As we look at the site periods are going up, okay? And again, those also kind of saturate out here. One thing that's really important to recognize, this is an important point that you have to deal with in model development, is that these site parameters are not independent of each other. They turn out to be strongly correlated. We look at these kind of things when we do this work anywhere in the world, so we're used to a certain degree of correlation, but the degree of correlation here is really quite extraordinary. So this is VS30 and site period. Again, if you have a higher VS30, you have a shorter site period, and VS30 decreases as period increases. And this is an amazingly strong correlation coefficient of minus 0.95. So it's a negative correlation. The LGC, the depth parameter, ZLGC, is shown here versus VS30. There's also a correlation, not as strong. And there's a fit model here, which is in this equation, that you can predict the mean depth given VS30. And I'll come back to that a little bit later, how we use that equation. So we had to have protocols for assigning VS30. So if we have a co-located VS profile, we use it. That applies to 10. And for the other 79, we had to use zone averages. The period was assigned from measurements. That was either the HVSR curves that I described earlier, or maps of site period from Lermo and Chavez Garcia in 1994, which was for 65 sites. We also used zone averages where we didn't have either of those. Okay, so now I'll go to the next topic, which is site response model for the Valley of Mexico. So you saw this figure earlier. This is a typical type of plot that we do. And when we look for nonlinearity anywhere in the world, Japan, California, Turkey, and we have recorded ground motions over a wide enough range of amplitudes, we always see it. Now, I know that that runs against the understanding, the beliefs, the practice that has been applied here for many years. I take the point from the presentation that preceded mine. That was having ground motions, oops, wrong button. That was producing ground motions a little bit lower than this, right, for that other earthquake, I think in 2023. But if you look at the very weak input motion records versus the stronger ones, you are seeing a decrease, but the decrease is only for high frequency or PGA, type records, also other high frequencies. It's not seen for long periods. The other thing I would point out is this slope right here, which is minus 0.27, is not as steep for zone 1 as it is for zone 3A, steeper. So let me just summarize the patterns that we see. We see that high frequencies exhibit evidence of nonlinearity, low frequencies don't. We see that where there is nonlinearity, it is weaker for stiffer sites and stronger for softer sites. That makes a lot of sense. Softer sites produce larger strains, going to produce more nonlinearity. That pattern, it could just be accidental. I mean, this is one earthquake. We usually like to deal with much bigger data sets. One earthquake is driving this nonlinearity from 2017. Maybe it's just accidental. But what I will say is the pattern here is exactly what we expect to see from first principles, and it's exactly what we see everywhere else in the world. So is Mexico City truly unique and different from the rest of the world? Clay is more plastic, after all. Maybe. Can't say it doesn't happen, but it shouldn't really surprise us if we look at a broader perspective that it can, in fact, happen here. So we need to deal with that nonlinearity in developing our model, so we fit it with the equation here, which is kind of a standard equation. You have amplification is this parameter, which is linear amplification, and this whole thing is for the nonlinearity. This is the slope parameter. It's basically the slope of that line. And this whole thing here is to transition from a horizontal line for weak shaking to the sloped line for stronger shaking. And this F3 is essentially a transitional amplitude going from flat to sloped, for which we used 0.01 G in this work. This is just what happens if you now do that across many different periods for all of the different zones, and it's just the F2 parameter. So what we see here is, and this is zone 1, so we see basically this pattern where it goes basically to 0 at long periods, and it's mostly at short periods. Notice the numbers here, about 0.2 to 0.3. Down here for zone 3C, more like 0.6 to 0.7. So much stronger nonlinearity in this case than this case. The red line is the nonlinear model that was developed essentially using the same process, but using global data in one of the NGA subduction models. And that model follows the pattern, more or less, that we see in Mexico City, but clearly the Mexico City case is different. And the levels of nonlinearity in Mexico City are noticeably smaller. That, to me, makes sense because, as Professor Ordaz pointed out, the soils in Mexico City are more linear than normal. Doesn't mean they're linear. Those modest reduction curves did go down. The damping did go up. They're not linear, but they're more linear, or they're less nonlinear. And we see that reflected through the values that you have here. And Professor Ordaz already pointed this out, but we want to be careful to not claim that we're the first ones to ever report something like this, and so these previous references are given here to Singh et al. And Sanchez-Sesma et al. Okay, so we have to remove the nonlinearity so that we can then focus on the linear part of the site response. So that's done by just subtracting the model prediction, basically this part of the model right here, from the within event residual. So this is going to affect the residuals for that 2017 earthquake, and we have a linearized residual right there. And then we basically look at those site by site. So I'm going to show this to you in several different forms. First, I'm just showing a few specific sites within different zones. So this is zone 1, 2, 3A, and this, well, 3A and B actually, and 3C and D. So there's several different sites here. This is the CU site, this is the SCT site, and you see kind of the expected patterns. Let me start here actually. So we have these strong peaks in the amplification out around 2 to 4 seconds. Here it's around 1.5 to 2 seconds. Here it's less than a second, and there's really not much of a peak here in zone 1. So you see those kinds of behaviors. My point in showing this to you is you can get the kind of behaviors you're used to seeing through these residuals analyses calculations. It gives you the same thing, basically. So I'll just highlight this CU site. As we've just heard before the break, that is the traditional reference site for ground motion modeling in Mexico City. And the point that I would make is that is not a typical reference site. It has a very strong site response. Okay, in natural log units, it's between natural log units, it's between about 0.5 and 1.5. In absolute amplification, that's factors of 1.6 to 5.5. That's kind of an extraordinary level of amplification to have for a reference site. And it does have a modest VS30 based on the velocities measured near it. So just to contrast this to more what I'm used to, right? Roger Borchert and others have used reference site approaches in California. The typical reference site is 700 to 800 meters per second, right? So much firmer site, and the site response is relatively weak for that kind of a site. So what I showed before was just a couple of sites. If we basically assemble all of the sites, we have the 89 sites, and we just break them up by zone. You have here the 6 zones. And you see that the site responses through this process are pretty consistent, right? So you see there's a fairly tight clustering within this zone, and so on. And you do see the change in periods that everybody is used to. I'll just point out that the one zone that has a lot of scatter is zone 1. Zone 1 has a lot more variability than all of the other zones. So if we think about it, we have consistent site responses in the different zones, generally speaking. We have variable VS30s between the zones. So it stands to reason that you could develop a first-order model for site response for PGA and these other parameters if you condition on VS30. So that's what's being done here. We have PGA, PGV, 2 different spectral periods. These are the individual site terms relative to rock, okay, the red symbols, bend means, and we have a model here. It's basically a bilinear model that has got one slope at low VS30s and a different slope at higher VS30s. Okay, so all the different zones are captured here, right? This is not a zone plot anymore. This is an intensity measure plot. We see a flatter at low VS30, steeper for PGA. For these higher periods, it's the opposite, steeper, flatter. Okay, so we have that kind of behavior, and the parameters here are just the slopes of these 2 lines. The other thing I'll point out, I wasn't going to mention this before, but since we just saw the presentation from Professor Ordaz, this is essentially kind of a global shift upward to match the data. That's that sort of regional effect that he was talking about, which we definitely see as well. So we have a model. It's a VS30-based model with nonlinearity. And what you need to do when you have a model is you need to assess it and see if it's working well. So to do that, you calculate residuals. So we basically, we take the within event residuals reference to rock for the linear case, and we subtract the model prediction, okay? And then we get a new within event residual, where now we're adding that V to reflect the fact that it's incorporating this VS30 scaling into the residual calculation. Okay, so that's the VS30 base model that I just described. I'm not showing you the residuals versus VS30. There's no trend. What I am going to show you is some effects of depth. And the reason we want to look at depth is not a direct parameter in the model, right? So when you make a model, it should, if you do your regression right, it should have no bias with respect to the independent variable you considered, VS30. What you really want to do is test your model relative to parameters you have not considered, okay? So in this case, we're looking at depth. The problem you have, if you're going to look at depth, is it is strongly correlated with VS30. And you don't usually, in statistics, it's not good to have such strongly correlated variables you look at together. We have lots of practice with this problem all over the world. The way that we deal with it, and we did it here, is, again, we have this fit line through the data. There is a strong trend of depth with VS30. So we don't use the depth itself. We use the differential of the depth relative to the scaling line. So this site here would have a positive differential. That site would have a negative. So if a site is unusually deep, or if it's unusually shallow, does that make a difference? The idea is that the average depth is already baked into the VS30 scaling model. Okay, so this is the equation for that differential depth. And there are some trends. They're not overwhelming, but there are some trends. This is one particular period where we see that if you are deeper than average, so more than 5 differential depth, the site responses are on average bigger. This particular period doesn't have anything happening at the lower values, negative differential depths, but some do go down here and are weaker than average. So those patterns are there and they've been captured. So once we capture those, we can now look at trends with period. So we were well aware as we went into this work that period is the preferred parameter. The zones are based mainly on period. People are used to period around here. So if we're going to have a model that is not specifically including period, we better make sure that it works with respect to period. So here we're plotting those within event residuals. Again, all the zones are here with different colors, 6 different intensity measures, and you're seeing the trends with respect to period. So like in this case, the pattern has no trend. We have bin means there. There really is nothing happening. All the short periods basically show that. PGV is pretty much the same. But there are some trends that we see. And I would highlight these two right here. So if we look at the 2-second oscillator period, and we look at site responses for sites that have a 2-second site period, we got to keep our period straight, right? This is oscillator period for response spectra. This is site period. And 2 and 2 are aligning. And when that happens, there is an offset. So our model is under-predicting the site response at 2 seconds when you are in these zones that have 2-second site responses. Likewise, we come down here at 3-second oscillator period, 3-second site period, there is a similar shift up. But a little perspective, I think, is in order here. So the misfits you're seeing in these two plots are about 0.3 in natural log units. That's about a 35% error on average across the sites. The absolute amplification at those same periods is about 3.5 natural log units, which is a factor of 33. So we could adjust the model. We've done this in other places. We know how to do it. We could adjust the model, make it more complicated, make you put in site period and VS30 in depth, and we could get a very, very small improvement in the model performance relative to the site amplification. We made the modeling decision not to do that, but we fully understand that others might not agree and might make a different decision, and that's totally fine. This is just what we decided to do. We did look at the 1985 records, and I should explain a little bit why this wasn't in the original data set. It was not used in the original model development, and the reason for that is that when you develop ground motion models, you have to have data selection criteria. You develop the database, but you don't use all the data. You have to have data selection criteria. One of those data selection criteria is that when the recording is far away from the earthquake, you may only be sampling the unusually strong records at that distance. So you have recordings, but you don't have the weak recordings at that distance. You only have the strong ones because you're falling below a threshold where you collect data. So there's weak ones you don't have, you have the strong ones, so you have bias. Okay, so this is called an Rmax criteria, which we applied, and if you apply that Rmax criteria for the 1985 earthquake, the distance cutoff excludes Mexico City. So we didn't include it. That being said, for reasons you're all very familiar with, Mexico City has an extraordinarily large site response, right? So it stands to reason that it would probably produce reliable recordings even at those large distances. And with that in mind, we went ahead and took a look at this as a validation process. So the first thing we did is we looked at the event terms for that earthquake, which were derived using the data within that distance threshold. And we see here, this is the sort of the range of event terms across all of Central America and Mexico. This is the average. And this is what that particular earthquake gives us. So up to about up to about 4 seconds or so, it's within -16 to +84th percentile. These are going a little bit beyond, and we see, these event terms here. So the earthquake as a whole is captured by the model fine outside of Mexico City. If we look at response spectra for a few zones in here, we can walk through this. So we have zone 1, 2, 3B. This might be mislabeled. That's probably 3A, 3B, C, and D. And what we're looking at here is the Parker model for rock. This is the recording in red. This is the model prediction in blue without nonlinearity. This is the model prediction with nonlinearity. Okay, and so you have all these different comparisons. Most cases, we are closer if we include nonlinearity than if we don't, but that's not universal, okay? So overall, this looks pretty good to us. There are sites where there might be some misfit, but as an overall population, we're doing a pretty good job. So now let's do a comparison of the proposed model with current models. That's essentially the SASID. At the time we did this, the 2024 papers were not out yet, so we're using this model here in the SISID program. So we used the version of that program from 2020. We accessed it for the calculations in 2022. These are just screenshots from the program that Victor collected. And we ran these calculations for ground motion stations in the Valley of Mexico with these site response estimates that I've described before. And we grouped the results by zone so we could visualize them. So I'm just going to walk through the sequence for zone 3B. So if we look at all the sites in our study that are in zone 3B, and we look at the SASID calculations, this is what you get. That's the mean of what you get across all those sites, or the median. This is what we get. You'll notice that it's quite a bit bigger. The peak is in the same place. The patterns are practically identical, but it is shifted up. So why would ours be so much bigger than the SASID program? Well, the reason is because our site response is referenced to 760. The SASID is referenced to the CU site, which, as we've discussed, has a very strong site response. So if you add that site response to the SASID, you get the blue line. I'm just doing that for the mean, for the median. And you see it's actually quite close, okay? If we go through and repeat that process for all of the different zones, you have the results here. So it's the same format each time. This is what comes out of the program. This is adjusting it up. And we see basically the same types of peak behavior that we see in the original program. The message from this is that the model that we've presented is not all that different than the model that you're already used to using. It is referenced to a different site condition, but it's capturing these peaks in much the same way. Now, a natural question, and we could talk about this more in the discussion, is why would a model based on VS30 give you a peak? In most places around the world, that's not true. Well, the reason, of course, is because the extraordinary, the fact that VS30 correlates with zones and the zones correlate with peaks. And we're basically capturing what's going on in those zones. It's going to naturally produce peaks. Okay, so just to wrap up some of the principal findings here, through the original NGA subduction database and the enhancement for Central America and Mexico, we have a state-of-the-art relational database. I haven't gone into what a relational database is, but it's a very efficient system for storing and querying information. Everything has been uniformly processed with uniform metadata assigned. So it's not like we do it one way for one period of time and another way for a different period of time. Everything is consistent. The value of this relative to a Mexico-only database is that you have enough information to constrain parts of the model for which you don't have enough information just in Mexico. For example, nonlinear site response, perhaps, or magnitude scaling over a very wide range, because notice that the overall database is going up to 9. Presented site information. In Mexico, it's extremely spatially non-uniform. Basically, we couldn't find anything outside of Mexico City. Once you come inside of Mexico City, there's this extraordinary correlation between VS30 and the site period. We've produced regionally customized ground motion models for Mexico. The magnitude scaling and the geometric spreading are from the global data. Okay. The regional features are the constant term that sets the overall amplitude, the magnitude breakpoint, and the fore-arc and back-arc anelastic attenuation. So these are the customized features here. In several of the plots that Victor worked out, there is a better fit of this global model with these regional adjustments relative to some of the Mexico-only GMMs. Again, I haven't compared to the 2024 versions, but for the earlier ones. The plot over here is not comparing to data. It's just showing some different features of models. This is for slab earthquakes, 300 kilometers, PGA magnitude. This is the local GMM, so that's Jaimes and Garcia Soto. It was mentioned by in the previous presentation. This is the NGA subduction. So you see there's some different scaling here. Notice the break out here. Okay, so a lot of times, in many places around the world, you don't see this break magnitude, and we don't see it in the slab models here either, but the break is most definitely there when you look at the global data, so it becomes important as you go to very large magnitudes. Nonlinear site response, we've already talked about that one. The CU station has a very significant site response. It is not a classical reference site. In terms of site response, outside of the Valley of Mexico, the global model seems to work fine, although there are some regions, as I pointed out, where improvement should be done. We have sub-regional or Valley of Mexico VS30 scaling model, so that you have to use, you can't use the general one. It's referenced to 760. We provide, for the overall population, very similar results to the current FAS-based model. And the code for doing all this is available at the web portal. So everything's open. You can go in, you can start playing with the coefficients, you can change, you can regress it in a different way if you want. Anybody can get into it and play with it. There's Excel spreadsheets and things like that that you can use there at the NGA sub web portal. So we see the advantages of this collection of models, the ground motion model and the site response model. is that instead of having one set of models for everywhere in Mexico except Mexico City and a different model for just Mexico City, there can be a consistent set of models for subduction earthquakes, including here. We believe that having ground motion models that do consider the broader lessons from the world to constrain certain features, that you are better able to extrapolate to hazard critical conditions that you may not have seen yet in the data you've recorded here. In general, it's better to use real valued site parameters, VS30, site period, whichever one you like, instead of discrete categories. The simple reason for that is, as you go from the boundary from one category to another, you get a step function. It's better to have a smooth transition. Real valued parameters give that. That's why we use VS30. And the framework I've presented here, including the fact that everything is openly available and you can tweak the code as much as you want, it more readily allows for application of site-specific or non-ergodic procedures. Obviously, I haven't talked about that, but that's where you really take a deep dive and you characterize the site response at your site. It could very easily be merged with just a customized set of F1, F2, F3 parameters in the overall framework to get a better prediction at a given site. Everything's open, both the data and the models, and anybody can use them and implement them and play with them. And what I've talked about here is in a set of papers. Both are Contreras et al. We have this one, which is the GMM for the whole region, and this is the one for the site response. And this is all my references. We benefited a great deal from discussions with folks here and from the extensive literature on site response and other issues in Mexico, so we appreciate all of that. So with that, I'm going to close it out, and I'm looking forward to the discussion.
Thank you very much, John, for this very nice presentation, very explicit and clear. So if you have any questions, please. We have time for a couple of questions. We're going to have the technical session in some moments, but if you have for some questions. Yes, please, Mario.
Thank you, Professor Stewart, for a very nice presentation. I was a bit surprised about the VS30 in here at the University City. The station is just a few steps from here. We can walk there, so you can see the lava flows. So, so 295 meters per second, it's too low. I'm not sure where this comes from, but we normally use for, well, it wouldn't be VS30, but it would be the average VS in the whole profile, more like 700.
Well, I don't have it right in front of me, but we have measured VS profiles at the site. So I'll be happy to share those with you after.
Okay.
So I didn't make that number up. We have that, and we have actually multiple measured VS profiles in different areas around Zone 1. But
yeah,
maybe the measurement
University
was
City, here.
Pardon?
This site, so
Yeah,
station, yeah.
As far as I know, the measurement was close to that site. Maybe
take a walk. Have a look.
Fine. That doesn't really mean a whole lot, but I would be happy to walk over there with you.
Yeah, I mean, we can look at the shear wave velocity distribution that was taken for calculating that VS30. We know that there are some side effects, important side effects in the university as well. I mean, this has been like documented before. I'm sure you know about that. But anyway, this is going to be one key issue for the discussion, but because if we're normalizing everything with respect to this point, this side, well, there's going to be some effect. So, and yes, please, Leo.
Thank you, Professor. It was very nice, very good presentation and insightful. I have one question. Professor Ordaz, and we know here that the pumping, the water system is based basically on the pumping of water, and we have consolidation and change in period. And the ground motions that you're using for Mexico City for your regressions account for that? Could it be possible that you are interpreting as a nonlinear term can be related to that consolidation? Or?
Well, I doubt it, because the data we used is from fairly recent earthquakes. Let me see if I can pull that up again. So these 3 earthquakes here are all since 2017. So I don't dispute that there are changes. I think that makes a lot of sense. What Professor Ordaz said, I don't doubt that there's groundwater drawdown. We see this all over the world. And if you're going to have groundwater drawdown, it stands to reason that the soil properties will change. You get different levels of matrix suction and these sorts of things. So that all makes perfect sense to me. I don't think that explains this, but it is an issue that means that a ground motion model you derive in 2025 might look different in 2050, right? So conditions could change.
Okay. Thank you.
Yes, Miguel. Sorry, this one.
Thank you, doctors, to our very interesting presentation. I'm Dr. Garcia Soto from the University of Guanajuato. Could you elaborate in simple words for the regional model? How did you infer the shear wave velocities based on surface geology?
Okay. How do the models that correlate VS30 to geology work, is your question, right?
Yeah.
Yeah. Okay, so I appreciate that and all the other questions. So the model that I'm using is Wills et al. 2015. It is from California. And it's a pretty simple statistical model. So he has many hundreds, maybe 1,000 VS profiles across the state. He has VS30s. He groups them into 17 different geologic units. Okay, so there's about 6 of those apply to different conditions and quaternary sediments, and the rest are different bedrock conditions. And he's calculating within each of those the mean and the standard deviation of the VS30. They're log normally distributed, so it's the natural log mean, natural log sigma. So that is one of several models that we use in California when we don't have a VS measurement. So you might then say, well, why would you use a model from California to predict conditions in Mexico? And that's a fair criticism. The short answer is we don't have a model in Mexico, at least one that we knew about. If we had one, we would have used it. We looked into, could we develop a model or at least check the Wills model? That's why we look so hard for VS profiles, even if they aren't at ground motion sites throughout Mexico, but we just weren't able to find them. It doesn't mean they don't exist, just we weren't able to find them. So this is not an uncommon problem. For a large database like NGA subduction, there are going to be data-rich regions like Japan and Taiwan, California, and you're going to have data-poor regions as well. So this is not unusual. The way that we deal with it is we take the model that we think is geologically most similar among the options that we have. We acknowledge that we have more uncertainty, and so I didn't get into this detail, but we have a field in the database that reflects the uncertainty that we think exists on the estimate. There's the scatter, but then there's the epistemic uncertainty, the limited knowledge uncertainty, which is high in this case. And so that's how we did it. It's suboptimal to be sure, but at least we're separating bedrock conditions from soil conditions, and we're separating lakes from alluvium and things like that to the extent that they are reflected on the geologic maps. The geology maps, I didn't really dwell on that. That's coming from, I don't remember what agency, but it's a geologic map that's available here in Mexico across the region. You may remember the particular map we used.
Yeah, it was from the Geological Mexican Service, all those maps, and surely share all this information with us.
Okay. Thank you, Doctor.
Yes, please, Miguel.
There's one more over here.
Thank you very much for the very nice presentation. If I'm not mistaken, you mentioned that at least like 28, 30 measured shear velocities profiles were employed, no? And related to Leonardo's question, at what dates does these profiles were recorded? Because if there is a significant time delay between the record and for a specific evaluation of an earthquake, you will have a big match that will affect the computation of the site-specific coefficients, no?
Sure. Trying to recall. I know that Professor Mayoral did some of those. We got some from a researcher whose name I can't remember in the U.S. He's in Arkansas. And I think he came down and did this work in the 2010s after one of the earthquakes. So it's not terribly old, but there are older ones too, right? So we got profiles, just a small in number, but we have a few profiles that go back to the 80s. So that was when Seed and Romo were working together, and in some of the reports from that period, there are profiles. So if we didn't have anything more recent, we used that. So those could be indicating lower velocities than you would have if you redid it now. Yeah.
Okay, yeah, they were after the earthquake, 2017 earthquake. So some more of the researchers came and do the measurements and everything. Yeah.
But you're using all the records, no? So the problem is the compatibility between the record and the profile, no?
There could be some of that. One of the tables in the Valley of Mexico paper lists every one of the profiles. Doesn't plot the profile, but it lists the citation for every one of them and how deep they are and what the VS30 is and all these different things. And the citation is there. So it would be easy to find out the range of dates. I think most of them are going to be in the last 10 to 15 years, but some are older.
Okay, thank you very much.
I think these are in the database actually, right? All the soil profiles and all the information is also available in the same web page.
It's in a supplement.
Yep. Well, now let's go to the next presentation, then we can have more time to discuss all these very interesting technical issues. So the next presentation is going to be, let me check the title. Thank you very much, John. You have the name of the presentation right here. The next presentation is going to be by Professor Morgan Muschieri, and he's going to talk about ground motion prediction models. Sorry, no, he's going to talk about ground motion modeling in the USA National Seismic Hazard Model. Model selection, combination, epistemic uncertainty, and discontinuity at the USA border Mexico. So basically how to combine all these models, right?
Yeah.
Thank you.
Great, thank you. Certainly first, thanks to the organizers for the invitation to present at this session. It's been really fascinating to hear about the complex ground motion issues that you face here. So I'm from the U.S. Geological Survey. I work on our National Seismic Hazard Model, and I'm certainly presenting on behalf of a large group of researchers, both folks that are in our offices now and going back through the many updates of NSHM. This has been an evolving process, and I'd like to just give you a sense of how we make these choices about selecting ground motion models or the ground motion prediction equations for our hazard models. I will go. Okay, great. So, okay, thank you. Today I've got just a handful of topics. I'm going to first spend a few moments reviewing some of the basic concepts of PSHA. I'm sure this is familiar to most of you, but I just want to discuss a few of those topics with a real focus on the ground motion characterization, which is our ground motion modeling component, and some of the details of the treatment of uncertainty there. Then the main part of the talk will really focus on two parts. First is our selection criteria for identifying ground motion models that we use in the National Seismic Hazard Model. And then second, I'll go through a number of examples from the different regions for how we implement these ground motion models. And we don't currently have a uniform implementation strategy, and so it'll give you a sense of different approaches that have been used, including some ongoing work where we've tried to harmonize those approaches. Finally, I'll just wrap up with some of the open questions that we've identified for consideration and details about combining models at boundaries. Okay, so PSHA, or probabilistic seismic hazard analysis, right, was certainly originated here in part. It underlies the seismic provisions for building codes in the US. Just in a very basic way, it consists of an earthquake source model or seismic source characterization, and then a ground motion model. It's important to consider both of these when we're thinking about the likelihood of experiencing strong shaking at a site, because there's both the contribution of how far away earthquakes are, what their magnitudes will be, how frequently they occur, along with what the corresponding ground motions are. And so these are combined through this hazard integral. Here's the kind of discretized version of this. And so just kind of broken up in a very simplistic way, the earthquake source or seismic source characterization is really telling us something about these event rates, and there we can loop over, integrate over all of the potential sources that are affecting a site. The ground motion model really gets distilled to this conditional probability of exceeding a ground motion at a site, and so we recognize that ground motions aren't just going to be a certain value, but have some distribution of values that we might expect, and there are these corresponding probabilities. So the focus, I think I missed a slide. No. Okay, so uncertainty for the ground motion, and here in this talk I'll just be focusing on the ground motion characterization. Uncertainty for ground motion in PSHA really considers two contributions that you may have heard of. There are two classes of uncertainty. There's an epistemic uncertainty and an aleatory variability, and so I just want to take a moment and describe our views or how that's implemented in our hazard calculations. So epistemic uncertainty is derived from, gets at the level of knowledge about some issue. So it relates to the uncertainties that can be reduced through additional observations. So some of these that can be important can tell you about the absolute ground motion level, as we heard earlier, magnitude scaling, distance attenuation, issues with site response. And so we certainly saw there are very different site responses that are observed across Mexico City and in other regions. In the way that it's implemented for seismic hazard, there are two kind of key observations here. I've just plotted two sets of GMMs. So you can see there's this cluster of GMMs. These are plotted as ground motion as a function of distance. There's this one lower cluster and then this upper cluster. These are actually GMMs for the lower set that are used in the western US where we have active crustal region. And in this upper cluster, these are ground motions that correspond to ground motions from earthquakes in the stable continental region in central and eastern US. In addition to these kind of offsets that are really getting at what the absolute ground motion level is in these areas, you can see that there are these very different functional forms that are showing up here just in the distance plots, and there are similarities that we've seen earlier in the parameterizations or the functional forms that they use, for example, in trends with magnitude, VS30, and all the different parameters that are used for ground motion modeling. The way this is implemented in PSHA is through this component that we saw earlier in the hazard integral. There isn't an additional summation symbol here, but we can use alternative models when we're carrying out our PSHA, when we don't know what the true functional form for this is. And the way that gets carried through in the hazard calculation, and here now these curves look similar, but here now I'm plotting this conditional probability of exceedance given a magnitude and distance as a function of some ground motion intensity metric, and so here it's PGA. So varying the median ground motions, for example, carries through into the hazard curves in the following way. So they all have similar shapes or similar slopes, but they're offset relating to what the median models are. And so this is how the median ground motions get carried through in the hazard calculation. The other uncertainty that I mentioned, and that's a key component of the hazard calculation, is this aleatory variability. This really has to do with this unexplained scatter that is seen after computing, for example, residuals from a ground motion data set in some region. This was originally just explained as a random variability in ground motions, and now there's a deeper understanding that there are repeatable effects in this ground motion scatter. And so I think a better way to phrase this that others have mentioned is that it's this aleatory variability is capturing both the random variability and the unmodeled uncertainties. So for example, if you're not including site terms in your ground motion model, they'll show up in the scatter of these ground motions. So the way that this aleatory variability is computed is through this expression for the conditional probability. So if we assume these ground motions are log normally distributed, this term falls here in the equation, also in normalizing the amplitude, and that carries through into the hazard curves that we get. Here are 3 examples with different aleatory variability values, but the same median value, and you can see that these aleatory variabilities affect the shape of the hazard curve or the slope. And so this has been noted for a while. And so I think now I've come to most of the equations that I'll be showing here, but these are important uncertainties that are considered in the hazard calculation. And just to mention that the rest of the presentation here is just going to be focusing on epistemic uncertainty and the median ground motions. Before I go on with the presentation, I do want to mention that there's this relatively new framework that's been implemented, was mentioned earlier, this non-ergodic framework, where you can really consider that the total uncertainty is given by but the sum of variances from epistemic uncertainty and aleatory variability. I won't go into the details of these calculations, but in terms of the mean hazard curve, which is what I'm showing in the black line for each of these calculations, the mean hazard curve is insensitive to the choice of how uncertainty is partitioned. And so you can either account for uncertainties in the aleatory term, or you can account for them in the epistemic term. And these different panels are different approaches for partitioning uncertainty differently between these 2 frameworks. Okay, so what I'll do now is move into one of these 2 main parts here for the discussion, which is our US GS selection criteria for GMMs. We've already heard a few of the pieces that are considered for selecting GMMs, and so just to be thorough, I'm gonna go through this approach. Certainly there's been ad hoc selection criteria that have been used going back to the 96 NSHM, which was the start of the kind of the modern era of hazard modeling in the US. We have a steering committee that recommended that we develop a set of criteria really following guidance of the national and international communities. So this has been a topic, so certainly we acknowledge that this has literature that goes back almost 20 years or longer. The criteria here follows some of this earlier guidance. We don't want this to be excessively specific because then you start to rule out ground motion models that can be useful because they don't fit within some specific criteria, but we need to have some kind of flexibility to incorporate these new changes. The applications that we are considering are really for ergodic ground motion models. Typically, this has been this 5% pseudospectral accelerations and then peak ground acceleration, increasingly peak ground velocities. But there could be some additional thinking as you move to alternative ground motion intensity metrics. So there are kind of four general classes within this selection criteria. We have some general requirements, requirements relating to the database for the ground motion models, requirements relating to the parameters and applicability of the ground motion models, and finally some requirements relating to their functional forms and modeling procedures that are reviewed as we move forward. And I'll mention that there are some pieces here. I took this from modified this from a 2014 report, which was the last time these were fully described, but there are some things here I'll point out that are already a little out of date and have been updated. Most basic is that the GMMs need to provide equations for the median and aleatory uncertainty of horizontal components. So essentially just saying that there are these published equations now. This includes tables for the metrics that are of interest. One I'm going to give you. Certainly we update these as our products evolve and we have new requirements. The GMMs have to be applicable to the seismotectonic regimes that are relevant for our hazard modeling applications. We require that the GMMs are published. This can be various forms. Certainly peer-reviewed journals, open file reports at the USGS, other publications. And an important part is really that the developers are open to working with us, both for the implementation of the equations and also to provide either code or verification tables, as I'll get to later. This we've found has been really important because often there can be changes from what's published in the papers, or we have some issue in reproducing figures, and so it really requires a time commitment from the developers because this is an important step. This uniqueness, because we use this weighted combination of GMMs, as I'll describe later, these need to be statistically independent. This has been difficult to quantify in some way, and we have some new approaches that we've been using. I certainly think this is a goal as we move forward with ground motion modeling. Data, we already heard about one of the more recent databases that was used for one of the NGA projects. But in terms of the database, these can be recorded, or increasingly these may be simulated databases. They need to be processed with uniform approaches that consider the important contributions to the ground motion intensity metrics. We also require that these be accessible to the public to allow verification and validation both by us and by other modeling groups, which we think is an important component for open science. In terms of the parameters and applicability, the models have to be have inputs for magnitude, distance, faulting style, at least for shallow crustal GMMs, hanging wall effects, site conditions. Currently the moment magnitude is the preferred magnitude. We have magnitude ranges that are required for the different seismotectonic regimes that are based on the needs for our hazard models. We allow for the GMMs to be reasonably extrapolated if the developers can provide guidance on that, and their models were developed over a more restricted magnitude range. The same with distance. Essentially here we're requiring that the GMMs be applicable to the distances that are relevant for our hazard applications. Because of the importance of faulting style or On ground motions for shallow active crustal, we require some modifications for strike slip, reverse, and normal faulting mechanisms. Similarly for that hanging wall effects that have been shown to be important in some of the NGA projects. Currently, NSHM uses VS30 as the primary site parameter for capturing site response, and so that's a really important component. We've worked with some developers to allow for some kind of relationships between VS30 and the underlying site classes that are used in their GMMs, and increasingly we've seen that most of the GMMs have used VS30, but this is an open question, I think, moving forward as to whether that's the most appropriate parameter for all areas. Functional form and modeling procedure, we also heard about this some earlier in Professor Stewart's talk. We have some expectations over the spectral shape and how spectral shape is going to vary as a function of magnitude, so we don't require specific selection criteria based on that, but do require that the models consider that. We require the models consider the magnitude saturation that we heard about earlier. That they consider frequency-dependent attenuation, so this is anelastic attenuation that may vary between regions in important ways. We kind of have requests that the model complexity not be overly complex, really relating to the implementation because we deal with many different models. And in terms of data misfit, the GMMs need to demonstrate that they are fitting the data set on which they were developed and that will be relevant for our hazard modeling. When applicable, we've been requesting that standard deviations include the within event, between event variability components that we heard some about, and as we move forward, there will probably be further partitioning of aleatory variability. So one of the important changes that's come up in the last few years is that we moved beyond just our very simple requirements for spectral periods, going from just a requirement for PGA 0.2 and 1 second and site conditions of VS30 for 760 to this much expanded set of both spectral periods and also site classes. And so this was really driven by desire from the engineering community for us to produce hazard maps for these different conditions, so multi-period and multi-site class. And so this is really increase the requirements for ground motion model developers, and this has really gone the way of the GMMs. Similarly, you know, we revise the selection criteria as these updates come in, either from kind of external requests for the hazard maps, and also as new knowledge becomes available about ground motion modeling. Okay, so in terms of the procedure for the selection of GMMs, just for an example, from Puerto Rico, we often have this iterative process where we're both evaluating multiple GMMs against each other, so in the absence of data, and then also evaluating the GMMs with data as required. We often look to previous NSHMs for input on the ground motion models that were used and similar studies. These 16 selection criteria that I mentioned before are used to identify kind of a suite of appropriate GMMs. I'll talk in a moment about this comparison with observed data, and then just the initial comparisons of the trends in ground motion models as a function of these input parameters. And so here, for example, is ground motion as a function of distance, as a function of magnitude, and a function of period. And we saw some of these plots earlier. These initial plots are really useful to identify cases where some ground motion models may be outliers. And so, for example, for this update of the Puerto Rico and US Virgin Islands NSHM that we're finalizing, one of the early models showed this very different distance scaling, which helps highlight an area that we need to focus on for data evaluation. This GMM, for example, showed a very different magnitude scaling, and it turned out that GMM had been developed on just moderate-sized magnitudes and didn't scale well at large magnitudes. I want to mention that we do have some tools available online. These are developed at the USGS, and so they typically only include the GMMs that we've implemented into our hazard models. But just to focus here, the types of plots that I showed in the earlier slide can be developed with these kind of graphical user tools. And similar groups are doing similar things. And so here's a similar example for these trellis plots from GEM, or the Global Earthquake Model. So this is kind of a standard practice for the regional hazard assessments. In terms of the consideration of ground motion data, for many of the areas where we're selecting GMMs, we are able to make use of ground motion models that have gone through kind of an extensive review from various community members, including the NGA projects. And so, for example, when we're implementing GMMs from California, there's been kind of exhaustive evaluation as to how well the ground motion models fit the data. But there are cases where we're looking at the application of ground motion models to places where they haven't been tested. And so this was the case for Puerto Rico. And so an important component of ground motion model selection for this application was compiling a regional data set and carrying out evaluation with the existing GMMs to identify whether they were appropriate or what the biases were in terms of ground motion residuals. And so the top left just shows the locations of earthquakes in the region. The earthquake locations are shown by these circles. The colors correspond to an event classification that we use, so whether they were crustal, slab, interface, or we may have some outer rise events in there. And then the triangles correspond to the seismic stations that we were able to collect. And so we put together this a nice data set. This is work led by Brad Agard. And so this is the kind of typical plot of ground motions as a function of distance and magnitude. And we collected something like 10,000 records for the region and associated with stations with VS30, both from measurements, HVSR to VS30 relationships, and then also from topographic proxy. For this case, we then do the same calculation that we saw earlier, this calculation of ground motion residuals, and so we look at the observed ground motions and subtract the prediction from various GMMs. We did this for a number of GMMs here. We're just looking at 4 of the GMMs from the NGA West 2 project. And as we saw earlier, positive, these are natural log values. This is kind of the average misfit effect. Positive values are indicating that the ground motions are higher than the observed ground motions are higher than the model predictions. Negative values are indicating that the observed ground motions are lower than the prediction. And so here we could see certainly centered around 1 second spectral period, we had this pretty significant misfit. And so this is a value of 0.7. So we're at factors of 2 to 3 lower than what the GMM prediction is. And I won't spend too much time on it, but there was an approach here to incorporate this into our GMM selection by modifying the GMMs that we used. So the kind of second part of the main part of the talk here, I'd like to describe to you are the ways that we combine GMMs in some of the different regions, and then some of our current thinking on harmonizing the implementation of epistemic uncertainty in NSHM. And so, okay, so what I'll say here is that the one common feature that we have across the seismotectonic regions that we're dealing with when we focus on conterminous US is that we consider 2 components in the epistemic uncertainty. So I know I mentioned there are the aleatory and epistemic, and so now there's also kind of 2 parts to the epistemic uncertainty that we include in all of our logic trees for the hazard calculation. And that's this between model uncertainty and a within model uncertainty. So the between model uncertainty is modeled in our hazard calculation by bringing in multiple GMMs, and I'll talk about the approaches for doing that. what we're doing there is we're really capturing differences in the way that the GMMs are parameterized, so the analytical expressions they're using for modeling magnitude scaling, distance scaling, all of these things. There are differences even within regions of the subsetting of data that developers use that end up being carried through into the GMMs that we've found to be important. The second part of this epistemic uncertainty in median ground motions is this within model uncertainty. And so this is really getting at an uncertainty that isn't captured just by sampling ground motion models that are available. So, this could potentially be addressed by sampling global ground motion models more carefully, but we've taken a slightly different approach. And so the philosophy behind including this additional within model uncertainty is the fact that although we have increasingly increasing numbers of records in these ground motion databases, the databases are still rather sparse at the larger magnitudes and shorter distances. And so we've all seen these types of plots of the representation of the ground motion data set. This is from NGA West 2, and so we include this additional uncertainty to say that there's the potential for differences from what's in the ground motion models that have been developed on these data sets. So basically, this is getting at whether or not large magnitude and short distance ground motions may be different from what's in the GMMs, and I'll describe how we do that. There may be unique source path or site effects or some combination of those things that aren't represented in the data sets currently that we want to consider an epistemic uncertainty, so we don't have big surprises for hazard modeling. So in terms of when I focus just on conterminous US, so just the lower 48 states, there are 3 different seismotectonic regions that we have to deal with. And for the last update of this model, which occurred in 2023, we had 3 different approaches that we took for epistemic uncertainty, and that's what I'm going to walk through here. So the first seismotectonic region is the Cascadia subduction zone, where we have both interface and intraslab events. The second is the western U.S., which is all areas west of this dashed red line, where we are modeling shallow active crustal earthquakes. And then the areas that are to the east of this dashed red line in the central and eastern U.S. is where we have earthquakes in stable cratonic regions. And so we're using different sets of GMMs and this different modeling framework for epistemic uncertainty. At the very end, I'll also describe some ongoing work in Puerto Rico and the U.S. Virgin Islands, where we've tried to implement a more consistent framework across the different seismotectonic regions. Okay, so one term that I'm going to be using for multiple regions here is this multi-model approach, and so I just want to be explicit about what I'm referring to there. The multi-model approach is essentially selecting multiple GMMs and combining them in a logic tree. And so as I described before, here are 4 different GMMs shown by these different colors that are plotted on top of a global suite, which is shown in gray. And you can see that the GMMs have different functional forms, so there are important differences in their near source amplitudes. They have differences in the attenuation. Some have this MOHO bounce, some don't. And so these are important epistemic uncertainties that we may want to consider. This is a typical approach that was used in all regions before 2018, and there's a new approach that we're using since then that I'll describe here. These typically are from different modeling groups, although they could just be different parameter choices from the same modeling group. Certainly, they're capturing some of the important ground motion features that have been observed in those ground motion data sets. One of the arguments against these is often that they can have this, these features of pinch points where multiple models come together. And so you can see the epistemic uncertainty or the spread of the models changes as a function of distance. And so it's high at these short distances. We actually have this kind of near pinch point where epistemic uncertainty gets very low and then increases again. And often we want to try to avoid these pinch points because they're essentially artifacts of the GMMs. Finally, there can be poor transparency of the weighting, the way that the weighting of the GMMs is carried through into the hazard calculations. So just to start, I'm going to walk through the three different seismic tectonic regions in our current modeling approaches. So in the western U.S. for these shallow active crustal earthquakes, we're using this multi-model approach, and so just here's a representation. We're using 4 of the NGA West 2 GMMs. Currently, these have equal weight, so these 4 GMMs then capture the between model uncertainty. The within model uncertainty was developed from the NGA West 2 data set by Resiliencia et al. This was following the publication of the NGA West 2 GMMs. The factors that we apply to the GMMs, which are shown here now, so each GMM gets these upper and lower branches corresponding to the 5th and 95th percentiles, have magnitude and distance dependence. So here the underlying principle is that ground motions for large magnitude events at close distances may have this additional factor of 0.4, which corresponds to 50% increase or decrease in ground motions. And then the relative factors in these different magnitude and distance bins relate to how many records are available in the data set. And so Resiliencia et al. Binned the ground motion data from NGA West 2 to come up with these scaling factors. And this is these are the factors that then get applied to the empirical GMMs independently. In the stable continental region or the central and eastern U.S., there's the main logic tree branch relates to use of the NGA East GMMs, and then a logic tree that was developed at the USGS based on a multi-model approach. And I'm going to spend a few moments going through both of these. NGA East was a product of NGA led by Christine Goulet et al. That first report, this summary report published in 2018. And before we go too far, I want to note that the mean curves from each of these 2 logic tree branches are relatively similar, but there are very different approaches to the epistemic uncertainty that are captured in the breadth of the models and modeling approaches that we thought was important to retain for hazard. So here are a sense of the epistemic uncertainty that correspond to these 2 curves. NGA East is shown in blue with all of the corresponding epistemic uncertainty shown in light blue. I realize this is a little difficult to see. Orange is the USGS developed logic tree from the seed models with its epistemic uncertainty shown in orange. So the key contribution of the NGA East project was to treat the distribution of median ground motions as a continuous distribution. This built on some earlier work that was applied to parameters, and here they applied this to the ground motions. And so essentially the log ground motions are treated as this multivariate normal distribution that can be represented by some mean vector in this covariance matrix. This gets pretty complicated, but the covariance includes 2 main components. First is this correlation model. The correlation model is essentially derived from the input GMMs, and so the NGA East project identified a set of seed GMMs that they use, and they fit it with this correlation model. They decided, however, that the models alone were not enough to capture the uncertainty, and so they used an independent estimate for these standard deviations or variance values. And so this is analogous to the within model uncertainty that we use in other regions. And this is a plot of the variance model that is used in NGA East. I realize these are difficult to see, difficult for me to even see, but this axis is showing magnitude, and this is distance, so short distances and larger distances. And so there are already some fundamental differences between the earlier model that I showed you from our Western US that was really just a handful of magnitude distance bins. They spent much more time developing this, but there are some key similarities. So first of all, there's high uncertainty that they assume at these short distances, although you can notice that they also have very high uncertainty that's occurring at these very large distances. And so essentially what they're capturing here is the potential for variations in inelastic attenuation across the region. They then use these two model components, so the correlation model and this variance model, and then they draw realizations from this multivariate normal distribution using a salmon mapping process that you may have heard about. I just want to take one moment and say that there's been a lot of focus on this, but essentially the salmon mapping is this dimensional reduction, and so the ground motions can be viewed as this ground motion distance pairs can be viewed as this hyperdimensional space, and so they wanted to identify a way to find ground motion models that had very similar trends in the GMMs, and the approach they settled on was this ground motion modeling approach. And so here's a kind of a simple explanation of this this method, which is essentially based just on this error function. Here is just focused on a three-dimensional trend, and so you can imagine if you had some cloud of points in 3D that's moving through space, it might be in some coil or something. There would be no projection that would really tell you about the most natural distance between these models, but this error function is able to capture these things. And so with salmon mapping, you can project onto some manifold, or in this case, a plane that pulls out the similarity between GMMs. And so in terms of the application to the seed ground motion models that they use here, here is the kind of a distillation of the similarity between ground motions from all of the input GMMs that they use. And so each of these black dots is a different ground motion model. When ground motion models are close to each other, that means that their values are more similar when in terms of the scenarios that they have looked at for magnitude and distance. And they spent quite a bit of time trying to identify the physical characteristics that gave rise to these similarities. And so they came up with the approach where they have these signposts or reference models. And so, for example, the blue triangles are telling you about constant scaling. So the ground motion models off to the right of this plot have higher ground motions on average, and the ground motions on the left side have lower ground motions. Yellow and red relate to the magnitude scaling and distance scaling, and so there's some way to start to interpret some of the physical characteristics of these. But I do want to mention or just highlight that this is really a statistical process, and that's been one of the that was one of the concerns at the USGS about this approach, is it's really heavily statistically based in assuming this continuous distribution. So once they've done this, the weights for each of these GMMs is divided up by the number of models that fall within each grid cell. And so you can see, for example, ground motion models that are very dissimilar from other models will end up with higher weights. The models that are similar to other GMMs get a lower weight in the sampling process. And then the basic piece here is that they then make draws from this continuous distribution to get a set of GMMs. Typically, they were coming up with 10,000 samples, and they divided this space up into 17 different sectors that were used for computing each of the GMMs. So what this meant was that they tried to develop a meta model. So they start off with some number of some set of underlying GMMs. They fit a continuous distribution to this using this multivariate normal distribution, make a bunch of simulations or realizations from that distribution, and then divide up the space in this salmon mapping framework to come up with GMMs. So because they have these 17 sectors, they end up with 17 different GMMs that are then appropriate for each of the magnitudes and distances that they use. I didn't include a slide here, but you can see certainly that some of the important information from the variance model carries through into these GMMs. And so at magnitude 8, there's much higher epistemic uncertainty in these GMMs than there is at magnitude 4, and that relates back to some of the assumptions that they use with the within model or variance models. The other approach, so the second approach that we use in the CUS is much more similar to what has been done previously. So it's a multi-model approach. There were a lot of discussions at our workshops leading up to implementation of NGA East as to whether we should just use the NGA East models alone or if they should be combined with another modeling approach. And in the end, we finalized on these two modeling approaches because there really wasn't a consensus within the community. I think there was some apprehension because the NGA East model development process is really complex and honestly I don't think was really appreciated at that time to be evaluated. But there were also real concerns that the model sampling had obscured some of the important features of the GMMs. And so, for example, some of the early versions of NGA East had no models that showed this MOHO bounce, and there were community members who felt that was a really important piece for various uses that they had. And so that was part of what motivated this alternative logic tree branch. And so this is a much more typical multi-model logic tree branch, similar to what we did for the Western US. Here we have many more GMMs because there were this whole suite of GMMs that were developed for NGA East. And then the weights really were partitioned based on some classifications of the models. And so it was an important component here was what the near source or geometric attenuation was like. And so we did some classifications of models based on near source classification. There were some consideration of spectral shape, whether these were single or multi-corner in terms of spectral shape, and then some consideration of the simulation type. And so many of the models in this area are from stochastic simulations. There were some that used FK simulations, reference empirical, and we wanted these to all be represented in the logic tree. The most recent implementation has been for Cascadia, and this is a much simpler implementation that was used. And so here we make use of the NGA subduction GMMs along with a couple of other GMMs that had been used in previous NSHMs. So the NGA subduction was obviously this huge effort with the most complete global data set and data set for Cascadia, which is an area obviously of importance to us. We use the Cascadia versions of NGA subduction. You'll note that we didn't only use NGA subduction. We used the Zhao model, and then also for interface, we used Atkinson and Macias. And this was really due to uncertainties about the future ground motions in Cascadia. And because we have no large magnitude events, these were really viewed as alternative and appropriate ways to characterize future ground motions. And so Zhao was developed from Japan. Atkinson and Macias is from a simulation-based method that was supported for use. There some of the earlier versions, I'm not showing them here, but showed that there were some pinch points in the response spectra that we wanted to avoid, and we were able to address that also by retaining some of these earlier GMMs. So unlike for the active crustal area, these GMMs included models for within model uncertainty, and so those were used directly with the GMMs, and so now you can see that the mean models are shown by the thicker lines, their uncertainties are shown by thin lines, and there are some different approaches that the model developers, both choices and features related to subsetting of data. An important piece here, however, was this distance dependence. I'll note that there was relatively weak magnitude dependence in this within model uncertainty, so that was not incorporated. Okay, so as you've heard, we have three different approaches to incorporating epistemic uncertainty. There are some common features in that we have included this between model uncertainty and within model uncertainty in all of the regions. But we'd like to move towards a kind of a uniform representation that we can apply across seismotectonic regimes that really honors those two contributions to epistemic uncertainty. And so I'm just going to take a moment here and tell you about the implementation that we have been working on for this update of Puerto Rico and the U.S. Virgin Islands. So here we don't have stable continental earthquakes, but we do have shallow crustal. We have interface events occurring on the Puerto Rico thrust and also on this Muertos trough structure. We have deep intraslab events associated with both of those structures. And so we've taken a different approach here to what's been done in the past. And so in contrast with the multi-model approach that's been used in a number of regions, here we're taking the scaled backbone approach. And so that's depicted by this plot here, where you have a backbone model that's shown by this red dashed line in this plot, and the uncertainty can be captured by some scaling factors that can be applied to the backbone model. There have been a number of ways that this has been implemented in other hazard models, and we're really focused on this approach because of its use in recent site-specific studies, and because it allows for a much simpler implementation. Here, let me check the slide. So for Puerto Rico, we chose a backbone. So now we just have one single model that's the backbone. That's our mean of these predictions. It's a weighted combination of GMM. So in this sense, it is similar to the multi-model. We're using the appropriate GMMs for each region. I won't go into how we selected those, but we capture some uncertainty through the average model in the magnitude scaling, distance scaling, VS30 scaling, and all of the other parameters that are in those GMMs. Alternatively, others have regressed functional forms to the regional data to come up with backbone models, or selected a single GMM. That was not the approach that we took here. In terms of the scaling factors then to apply to the backbone model, we use some of the principles that were described earlier from NGA East, and so we use all of the input GMMs for each seismotectonic region, and we do this correlation model fitting, selection of a target variance model, and then drawing realizations. And so the gray lines here are just 10,000 different realizations for this magnitude, plotting ground motion as a function of distance. Unlike NGA East, however, we didn't do the salmon mapping to produce 17 models. We wanted to just have a simpler representation of the ground motion characterization, and so we have the backbone model, and then we have one upper branch that corresponds to the 95th percentile and a lower branch that corresponds to the 5th percentile. So this is a procedure we've been carrying forward for this most recent update, and we'll see how it goes. One of the benefits of this approach is it allows for a little more direct comparison of epistemic uncertainty across these different regions. Previously, we couldn't do this because we had some relatively different choices in modeling approaches. And so this is the scaling factor, which corresponds to an epistemic uncertainty as a function of the spectral period. The different colors correspond to the different seismic tectonic regimes. And so really lowest epistemic uncertainty in the crustal, similar values for slab, which is shown in green, and the interface with orange, but some kind of interesting features that show up here that clearly relate to the underlying GMMs. So just to wrap up with a few comments here, I think the evaluation of epistemic uncertainty for our 2023 50-state update and for some of the development of the Puerto Rico and U.S. Virgin Islands has identified that there are some differences in the way that these within model uncertainty assumptions are developed that we'd like to reconcile as we move forward. So I think some of the main questions are whether these should have a magnitude dependence, distance dependence, whether they should depend on spectral period, whether they should vary between seismotectonic regimes. So for example, do we expect higher uncertainty of ground motions for active crustal regions where we have more data than we do in stable continental regions? I would say probably, but we haven't explicitly addressed that. Certainly there may be additional spatial variations that get down to this sub-regional classification that we haven't even started to address because we just deal with these relatively large regions for NSHM. And finally, there was some discussion in the planning for this about discontinuities at boundaries. And so one topic that I wanted to raise, because it can be important when you have hard boundaries, like when you implement some kind of zone in your hazard model and you want to be accounting for that in a reasonable way, that we do have an appropriate analogy for that, which is the treatment of GMMs at this western U.S. and central and eastern U.S. boundary. And so certainly we don't want to just use western U.S. GMMs right up to this boundary and CEUS GMMs right up to the boundary, because that would potentially impose this artifact that we don't think it's true. And we don't have enough data. Ideally, we'd have enough data from earthquakes in here to be able to constrain appropriate contributions from those GMMs. The approach that we've taken, given that, for this region is that we apply a spatial tapering function. And so we go from full weight on the Western US GMMs to zero weight as we cross over this boundary. And that allows for this kind of mixing of GMMs. And so when you have some arbitrary boundary that I think there's also epistemic uncertainty on, and here I'm showing two of the boundaries that have been produced in previous analyses. We don't want the results to reflect that type of choice. And so, one approach that we've taken is this kind of spatial tapering in NSHM. So just to summarize here, I'm wrapping up, I think, with time. So I think that you're all aware that the ground motion characterization for PSHA includes the medians, standard deviations, or aleatory variability, and their epistemic uncertainties. I hope I've stressed to you that at USGS we really view that the epistemic uncertainty in median has these two components. One that we can get at by selecting multiple models, but we also want to recognize that we may not have seen important contributions, whether they're from large magnitude earthquakes or unique features that could be due to velocity structure or source features or other factors. We have multiple approaches that we've used for implementing epistemic uncertainty in NSHM. This multi-model framework has been extremely valuable, and that's been the earliest and one that's carried through to today. We're also now incorporating some of these epistemic uncertainties that rely on a continuous distribution, implemented, whether through NGA East or through a scaled backbone. And I would say we haven't settled on approaches here, but this is an area that we're encouraged by because of some of the features that it allows, both for logic tree weights and for simplicity for users. So I would say a goal moving forward is a uniform, thorough, and transparent framework for epistemic uncertainty. We need to think more about the regional differences and how to incorporate those in our modeling, and what that means in terms of the evaluating the epistemic uncertainty that comes out. So thanks.
Thank you very much, Morgan. Since we're running a little bit out of time, and if you don't mind, we're going to leave the questions for the technical discussion. So can we have 2 minutes, 5 minutes to go to have some water and go to the restroom, and then we can see here again in 5 minutes. And the people that is going to be in the discussions group can come here and sit. And because we're going to start. Gerardo, please come here. Mario. Leo. ¿Nos va sentando? Voy a sentarme.
Yeah. I thought it would be useful to talk about it, and then I started something else like, oh no, I shouldn't.
Yeah, once you start talking about salmon's math, most people are like,
yeah, eyes glaze over. I know. I know. Yeah.
But I like that image. Was that from like a Wikipedia or something? The 3 zones?
Yeah. Mm-hmm.
That was
yeah,
very
you mean the projection or the dimensional
well, you
projection
have
one?
the 3D, and then you show the projection, and you can kind of see how they're different in the 3Ds, and you see how they're different in the projection.
Yeah.
So
Yeah, it wasn't Wikipedia, but there are a few implementations. I think it was like on one
Mario, si quiere.
Sácate si quieres para acá. Miguel.
¿Me llevo estos?
Miguel se fue. ¿Cómo está comiendo galletas? Voy a sacar.
Estaba afuera.
Si quieres echamos un poquito para.
Pero sí los dejo, ¿no? ¿Cómo van a saber quién está discutiendo?
Oye, ¿no ha habido preguntas y comentarios en el chat?
En YouTube.
Solo una señora puso manitas así.
Una señora puso manitas.
Sí.
Sí, revisa para que pregunte.
¿Puedo yo poner en el chat que...
Exactamente.
Sí. No. Aquí ya va a empezar la discusión. Paula, ¿puedes traer otras aguas? Más aguas. ¿Ya no hay?
Es que te doy la contraseña.
Ah. ¿Eh? Para ir transcribiendo. Sí, o sea, pues si quieres tú grabas el audio. Sí.
Sí, puedes llamarlos que se metan. Bueno. We're going to start. Could you please sit in? We're going to start with the discussion. Siéntate tú aquí, hombre. No seas penoso. Mario.
Mario, tú eres acá.
Tú eres aquí entre los.
Tú eres acá. Deje su mochila, nadie se va a
Espérame, de aquí el identificador.
Grab this.
Yes?
There were some papers set on my
Just
chair.
papers? Right here.
Oh, right here. Am I taking this whole couch?
Yes, you can sit here or here. I'll ask you with Mario.
I have to run to class. Nice to meet you.
¿No quieres estar en la discusión?
No,
¿O
tengo que
tenemos
ir a
considerado?
clase ahorita. 2:30.
Ok, bueno.
Mario.
2:30. Acabamos antes. ¿Qué horas son? Thank you. Thank you very much. We're going to start with the discussion session. Thank you for coming, the local expert and the people from abroad. I want to start by asking something regarding the uncertainties in modeling, the ground motion models. And this question is for Morgan. When you are selecting a ground motion model, what is the minimum things that you need to require to the model to be able to be included in your set of ground motion predictions?
Right. So yeah, we had this process that I mentioned with the selection criteria. I think that was the attempt at that time to capture the minimum requirements for a GMM. But I think there's still some fuzziness or gray area there in terms of what is desired. But essentially we want to select the models that are appropriate for application in the region and that give you some range of expectation in ground motions for future earthquakes. And so, I think certainly we need some multiple models at least to capture that uncertainty, just because we know that there are differences in attenuation on different paths, and there's some kind of variability in site response even at, for a given VS30 or whatever the site parameters are. And we want models that really capture some range of that variability for the hazard calculation.
That's very interesting. I don't know, Leo, here in Mexico, what will be the main difference between how we select our prediction models with respect to what is done in USGS?
Well, I guess that the answer Mario is the one who knows more about that estimation of the uncertainty of the selection criteria for the hazard mapping, because he leads most of the efforts on that. No? I don't know, Mario. What do you think?
No, well, we do something much more primitive than the process that Morgan described. So we fix. So it's more or less perhaps that what was done 10 years ago or so in the U.S. models. So fix the weights of the model based on qualitative characteristics. No? So size of the database and presence or absence of metadata, etc. So I guess that's the way it was done in many places some time ago. So we have not improved on those procedures, or let's say we have not changed.
Thank you very much for your answer, Mario. I want to just mention for the people that is watching us on YouTube, if you have any question, you can put it on the chat, and we will be very happy to also bring that into the discussion. As Mario was mentioning, data is important, and already Leonardo asked about more instrumentation. So regarding sites to be instrumented, here at the Institute of Engineering and at the Geophysical Institute, Gerardo, what do you think will be the best places to put more instrumentation to reduce the uncertainty in this ground motion prediction model that we see in a national level and also in the local level?
I guess there's this question of that you posed, Professor Stewart, of what is the back arc, which in Mexico is very difficult to define. It's a lot easier to define, for example, in Cascadia, where you have a very clean cut, if you wish, volcanic arc, and behind the arc you are in the back arc, and in the fore-arc from that region to the trench. Here in Mexico, it's very difficult because, for example, what you selected, and we discussed that once a while ago, as the back arc is really a depositional feature. It's not a tectonic feature. The southern margin of that wiggly line is more a depositional feature than a structural one. So I would think that we lack some stations to the north of the volcanic belt to really understand the attenuation. And even Mario, for example, showed that some stations to the north and to the west have this apparently high amplitude when you estimate the attenuation curve. So I would suggest going a little bit further north. We have very few stations to the north of the volcanic belt, and well, we'll talk about the volcanic belt perhaps later on. But that's where I would emphasize.
And also regarding this regional amplification effect that was mentioned in Mario's presentation, Eduardo, do you think that we should deploy more equipment in Mexico City or in Morelos? Where would you put them?
And thank you. Well, regarding that, I don't think that we need more stations in this zone, because we've seen that most of these stations are they behave very, I'm talking about accelerometric stations, not other stations. So we've seen that we have like 15 stations in the hill zone, let's call the hill zone in Mexico City, and they behave very similar. Apart from those in the north, very close to the Basilica, and some in the Cerro de la Estrella. And so we don't need more stations for that. Talking about Mexico City and the amplification and all that. I don't know what Leonardo or Mario thinks about this, but I think that we have too many stations in the lakebed zone. They behave the same for all earthquakes, so I think that it's worth moving some of them to other places where we don't know very well what is happening there. I don't know. We have very close stations in one single block, for instance. We can move one of these stations to another place, but not in the hill zone. I don't know.
Well,
Sit on, yeah. Just to comment something about the number of stations we have now in the city. 3 years ago, we had a big project to gather all the stations, and up to now we have 172 in the morning in the city. Most of them are in the lake, so we don't have that many in the hill zone, except for the ones we just installed in the Miscuac area that were acceleration stations, about 8. We have an array of seismometers that for other things we want to locate better and have tomographies, but for strong ground motion, I think we only have, I think we should put in the hill zone where we know that there might be some variations of the ground motion for local earthquakes, no? Because as Eduardo said, if we are talking about earthquakes that are coming outside the basin, it's probably not worth it, no? Mm-hmm.
Can I weigh in on this?
yes, please.
So one of the interesting things that Professor Ordaz mentioned, and I very briefly alluded to, is you seem to have this regional large site effect that is not related to the clays, right? There's something else going on. And so it seems to me that you need stations to figure out the geographic extent of where that is happening. So it must be happening somewhere. Maybe it's this volcanic zone, right? Mm-hmm. And maybe it's tapering off outside of there, or maybe it's a subset of the volcanic zone. But knowing where it is and isn't happening would seem to me to be a very important thing to discover. And I would accompany that with deep VS profiles, so you understand the velocity structure and what's driving some of these apparently side effects. Maybe it's something else.
Yes, I agree. There is a great need of knowing better, especially after Mario talked about this regional amplification, and actually was mentioned by Professor Sanchez-Esma. I think it's important to spend some time and money in keeping instrumenting those areas in order to characterize better, as you said, the geology and all these aspects. And at this point, I think that I like to hear comments from also the people that is sitting here, and in particular from Francisco, from Paco. I don't know if you can go deeper into this, because I think it's important to know if there is more to do regarding the characterization from the geological standpoint of this area.
Gracias.
Yes, I think I will continue over the line that I just start just hearing what Eduardo Reynoso mentioned, that perhaps some stations have not to be permanent. Maybe we have to move them and have somehow the example of the US array that was a kind of itinerary network that cover most of the territory of the US array. Maybe it will be interesting to know what Rhys Waller suggests regarding putting temporary, using the same instruments and placing them for several months and then move them. And then this will be very interesting project. You have a lot of stations, and we have gathered in some projects, and perhaps we can do, and in our regional scale with our forces, have a kind of Mexico array, a kind of just covering the parts in which you have doubts about the system, measuring for 3 months, say, then moving the array, and then slowly. It requires a lot of resources to move. We have experiments with the MASE project, was in collaboration with Caltech, and it gives a lot of results, a lot of scientific results of caliber. You know, it was Sholi Perez Campos working on that, and he did a very interesting contributions to the verification of some of the tectonic forecasts that made by Gerardo and others. Yeah, I think it's important to have a better knowledge of the structure, because this is, you know, maybe you remember the presidential address by Kayaki in the 80s when he was president of the Seismological Society of America. He said with the technology available, it was possible to forecast and predict ground motion. But then this is a preliminary requisite. If we know the configuration of the model, the configuration of the system, and this is the main difficulty. We have big modelers here. We try to model things, but we don't know the properties and the geometry of the system, so we have to guess. And for this is the main obstacle.
Just to mention something, in fact, the coordination, we just bought 200 nodes for doing tomography, but this is tomography, it's not recording a strong ground motion. They are forget the name, the ones that the small ones, the geophones, yeah, they're geophones, yeah.
Thank you, Leo. I don't know, what about the continuity of measurements? If we are moving the stations around, don't you think, Morgan, that can actually somehow limit the validity of the data because we can miss like a large earthquake? Or what do you think about that?
I mean, I think in the US it's been really powerful for tomography, for structure, especially with ambient noise methods. But yeah, I mean, there's always a chance when you move a station that you'll miss an important recording, and no one can predict earthquakes yet. So yeah, you're going to have some trade-off between where you put your instruments.
For instance, if we had only temporary instruments in Mexico City, we would have never seen the change in period, no, along the years. So maybe a combination.
You know, I think there is a potential in areas that have high seismicity, though, to really look at weaker ground motions if you're able to resolve those either with strong motion instruments or some kind of broadband like the compact trillium, because that can be really useful with these kind of residual analyses to help identify site terms. And so at least in terms of the site component, that could be a thing that you could, know if you have high seismicity rates in an area that you could start to at least map out linear side effects.
With these moving stations, we can map side effects. So that's interesting. That's a good use. What do you think, Eduardo, about this? So you don't believe that will be more that is important to have more data? Especially, Mario was saying something about the areas close to the basin borders, and also to measure local events, as Leo and Gerardo are working on that. Do you think that we need to put more stations in those clay areas that are close to the basin? Because as mentioned was mentioned by Mario, the 1D model is not working there.
Yes, but we need more students and people to work on that because it's a lot of work to, yeah. Actually, I mean, we have seen Station 84, which is very close to here. There were some collapses in the last earthquake. That station behaved very well, and it was very constant in both components of motion for many, many earthquakes. And all of the sudden, in the 17 earthquake, one of the components was up to 1G, and the other one was 0.5G. Spectra, yeah. And we don't know why. And we are sure, Paco, that it's a 2 or 3D behavior of the labeled zone, but still we don't have the hands to work on that and to model that and to understand that. So, okay, we can put more instruments and we will have more data, but we don't have hands to handle that, which it's another problem. But and all the Tláhuac Basin, the southern basin, it's full of very weird effects. It's really far away from the 1D behavior, really far away. So but we cannot model that. We don't know the data. We don't know the depth of the firms or the bedrock. We don't know that. You know what Tláhuac is? Tláhuac is in the southern part of Xochimilco. The very south of the. So it's good to have more data, but we don't have the people to work on that.
I have a question for Morgan. Maybe you are not the right person to answer, but since you are in the USGS and we are talking about instruments, so in our case, I think we have seen that in order to have more instruments, we can normally find the money to buy them. No, it's not easy, but it's possible, and we keep buying things. What becomes a real burden for the institute is the maintenance and the operation of the instruments. So how is that solved in the USGS that operates much more instruments than we do? It's just a huge budget every year, bigger and bigger, or technology has changed. What can you say about that?
Yeah, I'm not necessarily the right person to comment on that because I'm separate from the instrumentation kind of operation side, but I know there's a lot of thought given to when we decide to adopt instruments. And so certainly as USRA moved through, I think we had this opportunity to adopt stations into the backbone network, and I know that the USGS turned down some stations, which there was a lot of internal conflict about, but it was because they recognized there wasn't, maintenance costs are really high. So I can't answer that for you. I think that's a common issue. At the US level, we hear it from our regional seismic network partners that, sorry.
Thank you. I think, and correct me if I'm wrong, but first of all, you have permanent technicians, right, on staff, and that's their job. So it's not students. It's like technicians who are professionals. And 2, you've had infusions of cash for like earthquake early warning, right, which has broadened the network. Right. And so I think those are 2 key things. I'm not sure whether those are at play here or not, but it's helped in the U.S.
Yeah, there has been a huge build out in the western U.S. and Pacific Northwest that has been only due to congressionally appropriated funds. So they really recognized that there was going to be this need. But it's in other areas of the country where we haven't had that type of influx. There, the networks are relatively static because of those challenges.
Thank you. Here we have it's not as big as the stuff in New Mexico that you have in the USGS, but we have about 20 technicians that are operating the strong ground motion network. And in the seismological service, it's about the same number. And fortunately, we have funding from the university. So there is some budget dedicated for maintaining the seismological service, and we have a very small budget to maintain our network. So We are a little bit better than 10 years ago, where we have to get funding. Now we have a steady funding from the university. I don't think that happens anywhere else. For example, the Senapred that has stations, they can't maintain their stations. I guess they have to do a lot of turnaround the bureaucracy of the government. Other institutions don't have it. I think that the key thing here is that the USGS, a government institution, is leading the effort. Not UNAM, we're still a government institution, but we don't have the same power as the USGS has.
Leo, as the person that is in charge of taking all these recordings and everything here in the institute, what do you think it will be the proper way to go to start looking into having more instrumented size, more people involved in maintenance? Is been doing right now? Is something been doing, or we have to do something?
Well, we have a project in 2000. Prior to the big earthquake, we were working on a project with Xoli Perez Campos and the Institute of Geophysics on how to design the network. We have a proposal for instrumenting the entire country with a very dense network to fulfill two things: the better localizations, magnitude estimates, and do better shake maps. That was the objective in that case. So we have to revise this with the Institute of Geophysics. We are running the project now, and probably you're aware of that, Gerardo. We're installing stations this year, and next year we'll have to do some more. I think we have to review what we have proposed. And we also have to talk about this issue with other universities, no? CICES, Veracruzana, La UAM, all those networks.
So, and once we have the data, the next step will be to look at the models and what Morgan talked about, how to combine the models to reduce the uncertainty. So right now, the Institute is only using the approach proposed by Mario Ordaz. Is this correct?
No.
Is trying to move to a...
No, well, you mean for deploying the stations, the network was decided based on experiments that were run to respond questions about the wave propagation in Mexico. That's what I think it was. Since we started in 2014, every time we put a station is oriented to get better maps and to help the SSN, the Seismological Service, to locate better. So every station we have is shared with the Seismological Service.
And the shake maps are developed based on the traditional approach, essentially.
Well, we do the Bayesian approach that Mario developed. That is, we take the stations, and there are some. It's an algorithm that takes into account the location of the stations and the distribution of the. Basically the location of the stations, and there is a framework to generate maps, no? And the GMPs, not that you have already developed.
I think it's not too different from the way the USGS
is doing now.
Produces the shake maps.
Yeah.
So
now with the one that is being done, they are using now is pretty similar.
Yeah.
Yeah. Before it was different.
Yeah. So they start with a GMP, and if there are no stations, that's it. If there are stations, the GMP, the field is modified with some algorithms with the station readings, and then you get your shake map.
That's great. I mean, the similarities. Now, changing towards local events, Gerardo, what is being done right now? I know that you have been working in some attenuation relationship for local events.
Well, as some of my friends here know, I have been concerned with crustal earthquake on the Trans-Mexican Volcanic Belt. It's a very unique and in some ways very unusual tectonic region. The background seismicity is practically non-existent. I mean, we have, even in regions where there have been documented earthquakes, large earthquakes, for example, 80 kilometers from Mexico City, there was an earthquake in 1912. You go now, and there are several of us who have gone there. I see some others here, and put some stations and you record nothing. And yet, it lights up like a Christmas tree. All of a sudden, there's a magnitude 6.9, and then to the east there is another magnitude 6, and sometimes 6.4, and sometimes they're not unexposed faults. They're blind faults, which makes it very difficult to handle in terms of hazard assessment. You know, it's been hammered in my head by some of my neighbors, and I have the bumps to show it, that in order to construct a proper PSHA, you have to have a periodicity that you can use. And here, since there's no site, frequency matters. Yes, exactly. So it's a very unique area, and in fact, I was going to ask Professor Stewart, because what at least some of us have been doing is, instead of running a proper PSHA, because of these reasons, although some efforts are being made to include the historical data, as difficult as it is, to do deterministic models, simply to understand what the damage could be. And the problem is that we have had to use GMMs for the Mexican volcanic belt, GMMs that come from California, essentially, because we don't have any in Mexico, because it's difficult to construct them, because there's no seismicity. So I'm wondering if you think your estimation of GMMs, which is a general one for southern Mexico, could be applied locally to the volcanic belt, because again, we've simply gone and used those in California, which we believe is a similar region, and using a logic tree, see what the influence of changes in those would represent. So I don't know if you think, what do you think if we use your definition of GMM, which is for all of southern Mexico?
So I wouldn't use the same GMMs that I talked about today, because those are all subduction, but you could sample the crustal GMMs, and I think you'd want to put a large uncertainty on that. And one way that you might be able to get a gauge on that uncertainty is if you have seismic intensity data. So I don't know if you do or not, but like if some of these historical earthquakes, I think you said 1912, right? Going back many years. So if you have a feeling for the frequency of these earthquakes, that gives you an idea for the source characterization. And you know, it is very, very rough, but there have been efforts. Norm Abramson has been doing some of this to try to learn about GMM attributes using seismic intensity data. So I'd probably start with NGA West 2 or 3 models, and then see if you can adjust them based on that.
Thank you, John. Do you want to comment something, Leo, about this?
Well, it's related, because in fact I was going to ask Morgan, and now that Gerardo mentioned that we might need to do some modeling, deterministic modeling, but I believe there was a big effort in California to create hazard maps based on ground motion simulations up to very high frequency. I remember 5 hertz probably, or maybe a little bit less. And is that going to be integrated in these maps that you have? Are we going to do something similar here in Mexico?
Right, so certainly there's been this huge effort. You've been involved in the 3D simulations. So right now, the way that we've incorporated those into NSHM is through modifications to the empirical GMMs. And so in Southern California, for example, we have basin amplification models that were developed from the CyberShake simulations, but they essentially replace what's in the empirical GMMs. And I think our thinking is that is a framework that we could use probably for the next update too. So if we had enough confidence in the, some average feature, whether it's the amplitude, constant amplitude term, or some feature of the path attenuation or something, we could incorporate those. And I think it's particularly attractive in places like Cascadia, where we have very little ground motion data. But I would say we're still certainly not at the point that we're incorporating them directly, and that we recognize the need to really evaluate those and make sure that they're fitting observations before we move forward.
Yeah, so on the issue of simulations, we also use them in GMM development, and they're used, as Morgan mentioned, with the NSHM as well. And the key thing to realize is they're not used to set the level of the ground motion. When validation is done, it's usually shown that they're off by, oftentimes by pretty large amounts. But the scaling, I use that word scaling in my presentation, how does the ground motion change with something else that you can predict? Particularly if you don't have empirical constraint of that thing, then the simulations are a good way to do it. So you're adding a level of sophistication into the model that you couldn't otherwise get from the data itself. Mm-hmm. So that's kind of the way that we've used simulations. And I'll give you one very concrete example. So I was talking about the path model, and you have the near source part where it saturates. That is a very hard part of the model to get empirical constraint on. So in many of the NGA subduction models, we are constraining that from simulations. By the time you get a little further out, usually beyond the range of that near source saturation, then you have observations, and they're constraining the geometric spreading. So that's a very direct application.
I mean, I guess I would also mention, I think there are real opportunities when you're talking about complexities of 3D structure that might be repeated. And so whether it's this Trans-Mexico volcanic belt or other features, I mean, I think there are real opportunities to use modeling. And I know you've been involved in some of this work too, to kind of guide the functional forms or guide some kind of modifications for the empirical GMMs as we start to bring in more spatial complexity.
Thank you. Mario?
No, I think that Professor Stewart mentioned a very important point, which is that, or I interpret it like the simulations, regardless of the way with which you do them, have to be coherent with the GMPs. No, if you do simulations that are not coherent with the empirical observations, they are wrong. Mm-hmm. Now, what coherency means, that's a different story, no? But
good point. I don't know if you want to comment something, Jorge. You're okay. I thought that you raised your hand. Okay. Well, actually, I wanted to talk also. You also mentioned soil nonlinearities in your presentation, Mario, and I wanted to ask you if now that we have the new version for SACID, we have a return period of 250 years and 475 years, and the nonlinearity is basically associated with the shear strain that is undergoing in the soil during the earthquake. Are you adjusting for soil nonlinearities and the actual design respect or not? That's a question that I have in the new version.
Let me see. I don't actually remember. I don't think so. I don't think so. I don't think we are adjusting. No.
Do you think that you should? I mean, or you don't believe in soil nonlinearity?
No.
Well, I mean, Camille, yeah, I mean, you're saying like...
No. What I think is that, so my perception and my experience with interpreting data, etc. Actually, I wrote, the first paper I wrote on soil nonlinearity was in 1989. Wow, so I've been thinking about this
for a long time.
With Faccioli, with Professor Faccioli. So I've been thinking on this for a long time. But my perception so far is that we don't have a good method, good empirical indications to lead that, to guide that. And so far, it seems that the prudent decision to make is to keep it linear. The worst thing that could happen is that we over-design a little bit, which is better than under-design a little bit, no? So we are taking the prudent approach and, I mean, waiting or expecting for some better knowledge, better data processing in the future.
Well, in that case, I have a question for the geotechnical people. Could you look at the nonlinearity in the laboratory and test under pressure in approximately the ground conditions of the soils of Mexico City? I believe Romo did something like that, but I'm not certain. So could you do it, or has it been done in Mexico?
Actually, it can be done, but I want. Yeah, well, yes. I mean, there are standard tests that can be used to obtain the relationship between shear strain and the degradation of the stiffness of the soil. In fact, once I was talking to Romo, and he told me, Juan, I'm the responsible for people believing that the soil is linear, because when I published this paper in 1988, I mistakenly put the soil in Mexico City is almost linear, and then I put the G over G max curves and the damping curves, and then everybody thought that it was linear. But no, I mean, after a given shear strain, of course you're going to have degradation in the stiffness, and you're going to have soil nonlinearities. So this has been done. It's been done around the world, but yeah, sometimes surprised me that it's not taken into account in many analyses. So I don't know, the response spectra from USGS, do they take into account soil nonlinearities?
Nonlinearity? Oh, thanks. Yes, there's nonlinearity in all the GMMs that we're using, I think, and both in the median and in the aleatory variability in most cases. There are different treatments, and we don't have explicit logic tree branches because we just carry it through in the way that it's implemented by the developers.
And I guess that is
we take them into account outside Mexico City. So so my concerns are just with Mexico City. In other parts of the country, so what we are doing now with the national code, etc., it includes nonlinearity and more or less in standard ways, or the ways to which Morgan was referring to. But in the case of Mexico City in particular, there are experiments that can be made in the laboratory. So you can determine the G over G max curves and the increase of damping, etc. That's more or less standard, no? But when you use most of these curves in 1D nonlinear analysis, my impression is that the models we have and perhaps the misfit between the experimental values and the real values tends to overestimate the effect of nonlinearity systematically, no? Take the case of what I was showing, no? The 2017 event versus the 2023. The typical calculation we make is that you calibrate your stratified model with a small motion, so linear. Then you put it nonlinear, and you cannot get what you really observed during the big earthquake. So normally it's over-predicted. That's one thing. The other thing is that in the case of Mexico City, we have seen it many times, the spectra are very peaked, no? So very small mistakes in the layers, in the values of the layers, lead to very large differences in the computed values, very large, no? So the computations are very unreliable, no? You change, Manica has done it, he's not here. You change 10% one velocity, and then everything shifts, and the effect of nonlinearity is completely different, no? So that's my concern, and I can show the results that bring up my perplexity. No, and my opinion is that we should keep on the prudent side until.
Yeah, probably to work in some of the models calibrated for Mexico City clay will be a good idea here in the institute. You know, like spending some money if we have a question about that, and looking into the soil nonlinearities that is really well established, and actually internationally there are really good models that take into account this. I don't know about if you want to comment something about that, John.
Yeah, I'd like to make 2 points about this. So point number 1 is from a soil mechanics point of view, all soil is nonlinear. It just is. There's no such thing as linear soil. The question is whether it's here in Mexico or Italy or Greece or any number of places where there's local ground motion models and earthquakes that have been recorded in a small area. Have you seen it or not? Do you have empirical evidence for it? It is very common when you're looking at small data sets that you don't see it, particularly if you're looking at small magnitudes. Now, that's not the issue here. You have large magnitudes. They're just far away. So it is an extremely common problem in the literature that site response is modeled as linear, but it is for earthquake scenarios, magnitudes and distances that do not control hazard. And when you look at hazard controlling scenarios, which are much stronger typically, the level of shaking is much greater than what you've actually seen. So if you fit a model to what you've seen, you can very accurately capture the data, but it's not going to project well. We were talking at the beginning about, do you accept or you reject a given GMM? On all the projects I've been involved with, if it's a linear site response model, it's immediately rejected, unless you can plug in a different nonlinear site response model, because we're using them for hazard. We're not just using them to fit data, we're using them for hazard, and you need it because it's generally understood that soil is nonlinear and it's going to impact those hazard controlling scenarios. Point number 2 is more general than that. What we have here is a classic difference of opinion between experts. Very credible experts, I'd like to think. You have experts with lots of experience, and expert number 1 says one thing, and expert number 2 says a different thing. And my opinion is that's fine, no problem. Different people are going to have different interpretations, sometimes of the same information. Great. Now, what is your process for dealing with that? Do you say, well, we're going to pick winners and losers. We're only going to go with this expert, and we're going to ignore that one? Or do you have a process that says, all right, we have different expert opinions about something, whether it's nonlinear site response or anything else, let's have a process for ground motion selection that accounts for those differences. That is at the core of what Morgan was talking about. He has all these different ground motion models, all from credible experts, and they don't give the same answer, right? So they have a process for weighting them and, well, selecting them and then weighting them so that you're representing in the hazard those different outcomes. And if there's a message that I would just like to leave you all with, is I'd like to encourage you to consider doing something like that. Consider a suite of modeling approaches so that you're capturing these different expert opinions.
Thank you, John. Thank you very much. Now, moving towards local events again, I was wondering, have you taken into account to locate the epicenter here in the city, Leo? Have you taken into account also the underground mines that are located in that area? Do you think that is going to affect the underground mines that are located in the hill zone? Also the material that was just used to replace the material in the mines, and all of these underground cavities that we have there. Have you taken that into account for locating the epicenter of the?
Well, the procedures that are used in the seismological service, and Gerardo can correct me, are pretty standard. Worldwide, we use the same standards to compute the localization. So Most of the time, you use a 1D velocity model. Depending on the region you are, you use one or you use another one. You might be thinking about the implications of having hills, having mines. Certainly that will impact the localization, but for a national service, the scale we'll look at things is fine. It's like for Mexico City, we would be watchmakers. No? We're looking at a clock, and the tools we have for the national service is like a factory for doing, I don't know, something very big. So we know how to do localizations very precise. If we have a 3D model, that's already worked out. In the literature, there are tons of examples. People do it, but we have done it here at some instances, but it's not the common thing to do. Mm-hmm.
Thank you, Leo. So I think we're running out of time. It's 2:30. I don't know if you have any specific questions that I want to ask the speakers now that they are here.
I don't know if I can ask Morgan a question that he doesn't have to answer. What is the situation with the funding for the earthquake hazard program? Because I'm on one of the working groups for the Shake Alert, and I know there's a wide difference. I don't know where they are at this point, but during the last meeting there was a wide difference between the presidential proposal and the Congressional Appropriations Committee proposal. And I heard Gavin Hayes at the SSA dodge the question because he openly said, I don't really know what will happen. Can you mention something?
I'm going to dodge it too, but I mean, it often happens that the president's budget proposal is different than what gets worked out, and so it's like this is way outside of the area where I work, but the president's administration is signaling their priorities, and then Congress is going to have their priorities, and I think there's broad support for earthquake hazards. So, historically, going back to even when we had pretty significant cuts in the government, earthquake hazards has been supported across the aisle, so kind of bipartisan. And so I guess we're going to have to see if that carries through, but there are certainly natural hazards in all states and some pretty important lawmakers that support our work. So we'll see what happens. Sorry, I can't answer too much more.
Sorry.
Certainly have no input on it.
So I guess that's it, right? Any more questions? Let me just, before we close this, give you some letters thank you letters for everybody that came here. Only for okay. So, Professor Mario Ordaz, thank you for helping us. Eduardo, thank you very much. John, Morgan, and I'm missing two of them. You don't have them? Okay. Okay, sorry about that. See, I don't know. Let's take a picture. Thank you. Thank you very much. Thank you guys for coming. Thank you.
Thank you for all the discussion. Great presentation. Thank you very much.
Sure, sure.